really a pleasure to see another city today, and thanks for this opportunity. Today I am going to talk about crystals, and you may have seen crystals around many times, but most of the time we don't actually realize that many of them which are around us actually are crystalline. Okay, and so today I'm going to give you some brief introduction about crystals, and then you should be able to see the crystals much more around you after this talk. And so I will try to convince you that, and we can even engineer the crystals. Okay, we can design the crystals, and then through which we will be able to also design the properties. Okay, so that is what I'm going to show you today. So I work on a field called crystal engineering. Okay, I will also show you how we can engineer the crystals, taking some very simple examples, and then that should give you an idea on how we actually design the crystals in our lab. Okay, so that is what I will try to do today. So before going to the subject, I thank all my students and collaborators. And as you all know, we cannot, as a scientist, we cannot do everything that is possible, which is related to our research. So that is why we have to collaborate sometime. Like for example, if you have an interesting crystal and which could have a lot of interesting properties in some devices. So we are not experts in the devices. So what we do is we approach the experts and then we collaborate with them, and then quality of the work also improves a lot. And then you can really show that your crystals have some value. So that is why we collaborate with a lot of people, and this is only a small list, but we have much more number of collaborations. And also you can read this if you want to understand more about crystal engineering. This is a journal dedicated for crystal engineering subject, and so Crist Eng Com, this is how it is read. It is not read as crystal engineering communication, and many people read it like that, but this name itself is Crist Eng Com. So this is published by Royal Society of Chemistry, and so I am the editor-in-chief for this journal, and so this is what we publish. So we have communications, full papers, highlights. These are like reviews on the recent important contributions in the field. And then recently we also introduced basically a tutorial review, and since now there are so many applications in the field, but people are not publishing in these journals, and they are publishing in higher journals where everybody will see, because there is some application. So this will be of interest to a lot of chemists. So now research have started actually publishing in other journals. So then we thought, but still this is, most of these important contributions in other journals are based on crystal engineering principles. So then we thought we will collect all that and then put it like a tutorial review, and this should help the new researchers and students to understand these principles through just an article which is just which puts everything in one place. So this is a format actually that we have. So you can also read it. Not many have come up as tutorial reviews so far, and only I think maybe one or maybe a few are in the pipeline. So you will see more articles in this format. So this is a chemistry building in IIT Hyderabad. So this kind of reminds you of a periodic table, right? As you can see, so this is like a lanthanide, and you can see like there is a lot of similarity to periodic table. And in IIT Hyderabad, each building is basically after a theme. If you go to materials department, you will see like TEM, in the front you will see this corridor which looks more like a TEM. If you go to biomedical department, you see more like a helix, so each building is unique in IIT Hyderabad. And this is our guest house, and this is at IISER Kolkata. As she said, I was at IISER Kolkata for 15 years, and recently I moved to IIT Hyderabad. And so what is a crystal, right? Can anyone, I'm sorry, I'm going to trouble you a little bit. So how do we define a crystal? Can someone say? Well-defined three-dimensional packing. So what do you mean by well-defined? What do we mean by well-defined? You are absolutely correct. So how is it defined? Everything can be defined if you know the details, right? So just to give you an example, so this is a structure of a crystal. Can you tell me what is the structure? So I'll give you a clue. This is each sphere is a carbon. What is the structure? So this is very precious, right? So this is the structure of a diamond. So in diamond, carbon is connected to 4 other carbons, and as you can see, as he said, the location of each carbon is very well defined, right? So you see a translational symmetry, right? If you see there is a regular arrangement and the structure is very well defined, and so this is called a crystal. So in the crystal, constituents are basically very well defined, and you see a repetitive order, or you can say translational symmetry, and there could be many more other symmetry elements in the crystal. So when the structure has a translational symmetry in all 3 dimensions, okay, then you call it as a crystal. So hope I am able to, explain what is a crystal. If that is too difficult, so then I have another picture, and right. So this is not a crystal, but we are talking about the arrangement of molecules in the crystals, right? So if you see here, you have soldiers, in a very regular arrangement, right? If you see, if you have molecules, for example, you see that molecules have regular arrangement. If you see the distance in all directions, so you see a very much repetitive pattern here, right? So we can relate this picture to arrangement of constituents in the crystals. When there is a crystalline material, you see a very repetitive order, right? So then what is not a crystal? What is not a crystal? And this is not a crystal, right? Isn't it? Right? You don't have any. Can you see from the behind properly? I hope you are able to see. So here, if you see, in both the places we have humans, but here we don't see a very much repetitive order. So the arrangement of the people are randomly arranged here, right? So they are not on their, like everybody is basically in their own way, and then we don't see a repetitive order. So if you have a material, if you have a solid like this with this kind of arrangement, what do we call them? Amorphous material, right? If there is no repetitive order, we call those materials as amorphous materials. So we have so many materials around us, right? Which material is amorphous and which material is crystalline? So you have tiles here, right? So these are crystalline materials or amorphous materials. And which is more stable? Crystalline material is more stable because each one molecule is able to go and sit exactly in the optimized position, right? Everything they basically go and sit in the most thermodynamically optimized positions most of the time. So that is why they are more stable. Amorphous materials are not more stable compared to the crystalline materials, right? That means most of the materials should try to go into crystalline arrangement, right? So then if you look at basically tiles or stones or metals that are around, most of these, even sand, anything that you see around, most of them are actually in the crystalline form. But these are not single crystalline. Okay, they are not single. Single crystal means all the molecules have exactly the same orientation. So if I have a grain here, this may have one orientation, but I may have another crystallographic grain which may have a different orientation, but within that there is a regular arrangement, right? Most of the materials around are polycrystalline. So the grains are not exactly with the same orientation, although each grain is highly crystalline. So grains may be completely oriented in a different way. They are called polycrystalline materials, but they are crystalline materials. Most of the materials which are around us are polycrystalline materials, right? Suppose if you take wood, there some component may be crystalline, but most of the biological materials have very less crystallinity. Okay, so this is, but other materials, for example, if you take our bone is a highly crystalline material. Our teeth is a highly crystalline material. So there are many materials which are around us and which are also crystalline, right? So if you look at crystalline state, we all know that in the solid state everything is frozen, right? In the liquid there is a lot of movement, but there is a confinement. But in gases, molecules move freely everywhere, right? So this is how we imagine different types of different forms of the materials. But if you look at more carefully, so even in the crystals, molecules are not completely frozen unless you go to 0 Kelvin. Okay, there are always thermal vibrations, right? So this is how we see different states of matter. So here you have a solid which is highly crystalline, and then you have a liquid. Suppose if you solidify the liquid without, allowing them to basically go into order nature, so that will become an amorphous solid, right? If you just flash cool it, you don't allow it to crystallize, so that will give you the amorphous material, right? But most of the time it is very, very difficult to have a amorphous ice, right? So it's always crystalline ice what we have, right? So it may be polycrystalline. Then you have gases. In gases there is a lot of energy, and then molecules actually move in all possible ways. So this is how we basically compare different forms of materials. So why crystal structure is important? Is it really important to understand the properties of the materials? So we have seen the crystal structure of the diamond, right? So this again, I'm showing it here, the crystal structure of diamond. We all know diamond is one of the stiffest materials, right? So, and if you want to cut something, so you normally try to cut it with the diamond, because this can cut other materials because it is more stiffer compared to all other materials. So you can use it to cut. But we never use graphite to cut it. So, but we all know that both are from the same material. Both have carbon only, right? What is the main difference? The main difference here is carbon is connected here to 4 other carbons. So carbon-carbon bonds are very, very strong. So that is why diamond is really stiff compared to any other material. But if you come to graphite, it has a layered structure, right? In one, between the layers, you have only van der Waals interaction. So they are quite weak. Obviously, this material is not going to be as stiff as the diamond. So we are able to explain the mechanical properties using the crystal structure, right? Suppose if you have a way to control the crystal structure, not here probably, but in some other material or any material, so then we will be able to also design the properties. So this is called crystal engineering. If you are able to engineer a crystal structure, and then if you are able to engineer the properties, so then this you call that as the crystal engineering. So that is what we do in our lab, and mostly we try to engineer crystals of molecular materials, right? So these are different materials, same elements you have, and different structural order, different properties, and so that is why they are completely different when we look at from the property point of view. So then there are many crystals around us. So this is basically a salt, right? A grain of salt, and there are many, many crystals, and then sometime if you are not very lucky, you may have a crystal in your kidney, right? So these are kidney stones, which are also crystalline materials. When you have a lot of minerals, so they can actually crystallize, right? So I hope all of you know how to crystallize materials, and we don't want to always have crystals everywhere, but so even the stones which are in the kidney are also highly crystalline materials. So most of these are polycrystalline. So but if you look at the kidney stones, they have many, many minerals, not just one component, but there are not just uric acid, but there are many other components which also can go into the crystals. So it's kind of a doped crystal, you can say, right? So, and people have known crystals for long time, and many of you might have some of these, shiny and colorful crystals on your ornament or on your fingers, right? So these are all actually crystalline materials which are there everywhere around us, right? So, so people have been using crystals for long. So if you are looking at the properties of the crystals, then you have to go and then look at how each molecule is interacting with other molecules. As I have shown in the case of diamond and graphite, the structure determines the properties of the material. So if you want to talk about the properties of the material, and you not only look at the crystal structure, just molecular entity, but you also look at how they are connected with each other. And then that will allow you to explain how the properties are dependent on the crystal structure, right? So for many applications, you need to have the crystal structure, and once you have the crystal structure, you see full molecule, and then probably you will be able to also see how these molecules are connected and what kind of intermolecular interactions are there, and all kinds of information can be obtained from the crystalline once you have the crystal structure, right? So, and this is crystal of a sodium chloride, okay, table salt, right? If you see here, this is the a few unit cells together, what I am showing here. Do you see any similarity between the shape similarity between these two? They look very similar, right? So it looks like a cubic, and this also looks like a cube, right? Why is the similarity? So because when you have a cubic unit cell, and then if you try to pack all of them, and then you basically are going to get exactly similar kind of a shape. For example, if your box, unit cell box is tilted, or it is unsymmetrical, when you pack them, you get, when you grow the crystals, you will also see that reflected on the morphology of the crystal. And particularly when you have a cubic lattice, so all the faces have exactly the same kind of surface. So that means surface energy of all the faces is exactly same. In a cubic crystal, you have, because of the symmetry, so all the faces are equivalent. So when new molecules or new ions come and then try to, sit on it to grow in the process of growth, when they approach the surface, either this surface or this or other surface, will be, kinetics will be exactly same, thermodynamics will be exactly same. When that happens, so the growth of all the faces will be also exactly same. When growth is same for all the faces of a cube, then you get exactly like a cube. For example, if the growth rates are not same, if your symmetry is lower, for example, if you take a triclinic unit cell or monoclinic unit cell, so one phase is different from the other phase. So the growth may be different for each phase. Then maybe you get a long crystal or a plate-like crystal or completely a different morphology. So it all will depend on your unit cell, and then how these are, all the phases are basically connected with the symmetry. What is the symmetry? So if the symmetrically they are all same, then they will behave same way. If they are completely different, then the growth also and all the properties, surface properties, wettability on these surface properties, how they interact with solvents, everything will change. Okay, so that is how from the unit cell you will be able to explain not only the morphology, you will be able to also explain many properties of these crystals. Right, these are the unit cells. So this is a simple cubic, and this is a tetragonal, and this is orthorhombic, rhombohedral, monoclinic, triclinic. In case of triclinic, all the angles are different from each other, and then all the lengths of the unit cells are also completely different. In case of the cube, so all the alpha, beta, gamma are 90, and then A, B, C are also equal with each other. Right, that is the cubic unit cell. So now I have another question for you. So now can you tell me which one is a crystalline material? Second one? What about the first one? First one is also crystalline material or not a crystalline material, or we can't confirm? How do we define a crystal? Not based on the size of the grains. For example, if I take salt, I grind it. Then I take a small speck of it, and then I put it under TEM or SEM. I might see very big crystals, right? So since we can't see them, like a proper crystal, which we always want to see, so we cannot say whether it is actually a crystalline material or amorphous material, right? Suppose if I take glass, okay, glass is amorphous, all of you know, right? So if I take a glass and then make it into small powders, it might look like this. But if I take salt and then grind it properly, it might look like this. Making an amorphous material is very, very difficult. Okay, so by looking at this, we cannot tell. So here actually in this slide, both of them are crystalline materials. So the best way to know whether it is a crystalline material or not is to put it under a X-ray diffractometer or powder XRD. If you take a powder XRD, if it is crystalline, you will get sharp peaks, right? If it is an amorphous material, then you get a very broad hump, right? Only that can tell you whether it is crystalline material or not. Not just by looking at the morphology, we will not be able to actually assess whether it is a crystalline material or not, right? So most of the time we grow crystals, very good crystals, and to get the crystal structure, right? So that is what we do. If it is a crystalline material, you will see nice diffraction spots if you are using the single crystal XRD, and if you are using the powder XRD, and normally you just show only the peaks, right? And that is what you show through powder XRD instrument. So then there is something called polymorphism. Okay, as in case of carbon, we have many allotropes, right? We call them as allotropes because the element is same, but the structure is completely different, right? But if it is a molecule, let us say paracetamol, many of you might have prepared it in the lab or you might have taught it to the students, right? So paracetamol is a small molecule, and what happens, is it possible for it to also crystallize in different arrangements? For example, if I take a brick, I can pack them in a normal way with a slip stack, or I can put bricks on one over the other and then make a wall, right? So I can arrange the bricks in different ways. So using molecules, can we also build different crystals? If we build different crystals, that means same molecule is going into different types of packing, and then that gives you a crystal. So do we expect the properties of such crystals to be same or different? If a molecule is going into different types of arrangements, okay, the properties will be same or different? Properties will have to be different because interactions are different, energies might be different, lot of things might be different, right? So the properties will be different. So if you can control how they pack, then you can also control the properties of the material. For example, I take a pharmaceutical crystal and then I make one particular crystal packing. Then I also make another one. For example, other one is much better in terms of solubility. Okay, then maybe that is better for a pharmaceutical formulation compared to the other one, right? If I can control the way they grow and then the way they pack, then I will be able to also control the physical properties of the pharmaceutical materials. And I am sure many of you are also studying some courses on the pharmaceutical materials. So I will tell about this polymorphism. So if a molecule crystallizes in different packing arrangement, we call them as polymorphs. Okay, many of the APIs actually have many polymorphs. Okay, paracetamol also has polymorphs, and aspirin also has different polymorphs, and many drugs have different polymorphs. And these pharmaceutical companies want to crystallize the most suitable ones. They have to be stable, they have to be very good they should have very good solubility, and then many other properties like tabletability, flowability. There are many things that can come from the polymorphism. So let us see, for example, if this is your molecule, each box is a molecule, and then now we try to pack them and then make the polymorphs. So how do you do that? As you can see, the box is same, but the way you arrange them is completely different. So these different arrangements are called polymorphic forms. Okay, if you have a molecule which is going into different types of packings, molecular formula is exactly same, molecule is exactly same. When you have this, then you call them as polymorphs. Okay, do we see polymorphs somewhere else? Have you come across any polymorphs in your daily life? Right? So you may have actually seen many polymorphs, but we do not know that they are polymorphs, right? So all of you have, eaten this, right? So how many polymorphs do we see for this? So this is a, main ingredient in chocolate is cocoa butter. Okay, so this actually can exist in many polymorphs. And sometimes, you see some chocolates don't melt very easily, but some melt very easily, right? You may have seen. Some melt very easily, some, you know, even if you keep it outside, they are much stable. And also taste sometimes is very different, right? So it has many polymorphs. As you can see, the first polymorph has got melting point of 17.3 degrees. So if you keep it outside, it will melt. And the other one is 36. The last one is sixth polymorph is having a melting point of 36. Okay, if you have this polymorphic form, maybe at room temperature, you know, particularly inside the room, it should not melt. But if you have a other form, basically, like, you know, these one of these forms, maybe they will start melting at the room temperature. So it has got many polymorphs. And as you can see, most of the time, the crystals, the polymorphs that basically, you know, the chocolates that have this polymorph, you know, form 5, so which are reasonably stable at room temperature, and also this gives very nice texture on the crystal, on the chocolate, and also it melts very easily in the mouth. Okay, that is why the companies, chocolate companies, want to make only this polymorphic form. What they do is they actually heat this composition above room temperature, and then just, you know, they try to crystallize slowly within this temperature range. Okay, then you don't get all these because they are in the melted form. They can't basically crystallize, and then slowly you crystallize it, and then at a 33 degrees centigrade you try to keep it, and then you actually get this polymorphic chocolate. So then they nicely, then they look very nice like this. So sometime, you know, there could be a polymorphic transformation. So this is having higher melting point, right? Form 6. So can it convert into some other polymorph? Maybe more stable one. Higher melting point means more stable, because to break these bonds, you need more energy. You have to go to higher temperature. That means somehow it has got a much more stable structure, and then to basically disturb it, you need more energy. That means it is more stable. So higher melting point means it has got better stability. So if it has got better stability, then any form that is less stable should convert also to this one. There is a good possibility, right? If you have this chocolate, and this actually may convert into the more stable polymorphic form, right? When that happens on your chocolate, you will see something like that. So have you seen something like this? Like white patches blooming, you know, this blooming will be seen sometime when the chocolate is kept in the fridge or, you know, outside for a long time. So you see this actually kind of a white patches. So this white one is actually the most stable polymorphic form, and also the taste also won't be very good. It becomes little bitter. It's not a fungus or something else most of the time, but it is just another polymorphic form. Next time when you see your chocolate something like that, what you do is you, on a flame, just you basically move it a little bit, and then you see that it again goes back to the original texture, and you will see that this disappears. So that means you are converting it into another polymorphic form. So you can do this test at your home when you see a chocolate something like this next time. Okay. So how do we grow the crystals? So normally if it is an inorganic material, you do it at high temperature, but I am not going to talk about the inorganic crystals. I am going to talk about only the small molecules, like it could be a simple salt, or it could be an organic material, simple organic molecule. So let us see one video where it is clearly explained how these crystals are grown. This also can be done in the lab. If you have copper sulfate, you can also buy the copper sulfate in Amazon. Like, you know, this is a, so you, you take copper sulfate, and then you, so you have basically, you can grow very big crystals like this. So what you do is, you take copper sulfate or any material that you have. If it is a small molecule, then you take it and then you dissolve it in the solvent. If it is soluble in the water, you can dissolve it in the water. And so here it is pentahydrate of this copper sulfate, and you take it and then you put it, basically dissolve it in hot water, and then you nicely shake it so that everything dissolves. And once everything is dissolved, you have to heat it normally, and then you properly dissolve it, make a clear solution, then you filter it after making clear solution. So once the solution is very clear, add as much as possible. You have to make a super saturated solution. If you don't make a super saturated solution, so crystals won't come, right? You have to make it super saturated. When water slowly starts evaporating or starts cooling down, when you make it very hot, you can actually dissolve much more, right? So when you keep it hot and then make a super saturated solution and then leave it, and you can actually add few seeds if you want to get the crystals fast. Then you take out these crystals, then take one very good crystal and then you can use it as a seed. You can hang it inside the saturated solution. You make another solution, you dissolve everything again, just take one crystal, good crystal, then you hang it inside, and then you can actually keep doing it multiple times, and then the crystal grows, the seed that you have grows bigger and bigger. So you tie it a rope, small thread, and it could be just a cotton thread or a nylon thread, and then you put it inside the solution. So you hang it. So this is potassium chloride. This is another crystal which also can be done, or this is called alum normally, which also can be bought on Amazon. If you want to demonstrate crystallization to students, school children, this is a very good experiment. I have done it many times in my lab. So then you take this solution, again you heat it, add more compound, make a clean solution, and then again bring back the seed and then put it inside. You keep doing it multiple times, and you keep again, then crystal will keep growing bigger and bigger. Okay, so then you can make as big crystal as you actually want. So as you can see here, it's a nice crystal, right? So you can grow very big crystals if you give enough time, and then if you actually have enough material, right? And with more cycles, it will keep growing. So you can go on growing very big crystals. Okay. So this is the copper sulfate crystal. You can also use this. I think this is a polish, nail polish. If you put it little bit, it's a transparent one, and it will remain for a long time. And this is alum crystal, KCl, and it is, as you can see, the shape of the crystal is very different, right? That means this unit cell is different for them. Symmetry is different, right? As you can see, this another one looks more like a cube. KCl looks more like a cube, and this looks completely different, right? This is see how beautiful it is, right? So this can be easily grown in the lab if you want to actually try it out. So now the question is, how big can we grow the crystals? So is it possible to grow them really big? So then nature can do a lot of interesting things, and you will see that here. So these are crystals. This is not a movie from the cinema or something. You can see there is a cave in Mexico, and where you can see very, very big crystals inside the cave, in a cave. Okay, this is in Mexico, and so there was a lot of basically salt water inside, and then temperature was also quite high, and this is actually grown for hundreds of years. And then as you can see, this is basically the cave is below this field, and scientists have actually evacuated all the water, and they basically went inside and they filmed it, and crystallography team went inside, and then they have actually seen that there are quite big crystals, and crystals can grow to whatever size you want, as long as you have enough time and then enough material. Okay, so as you can see, these are really, really big crystals, right? So right, you can imagine like how big are these crystals. So these are all inside a cave. Okay. So how do we engineer the crystals? I will talk a little bit about the design of the crystals, and I will show you the strategies that we use in our lab normally, and then I will close my talk. Okay. So how do we design the crystals? So we all know engineering of bridges, civil engineering, electrical engineering, right? And there are a lot of traditional fields where engineering is common, and we know how those are designed, right? You need materials to engineer, and then you need to have a plan to connect these materials, right? Or it could be a software design, so you can also have engineering in the design as well, right? So here in our lab, what we do, we take molecules, and then using molecules, we actually engineer the crystals. So to connect the molecules, you need intermolecular interactions, right? You need to use the intermolecular interactions to design the crystals. So we take molecules, we design the molecules, and we synthesize them, and then we put certain functional groups on the molecules so that the way they make bonds, non-covalent bonds, the way we want. So that is why we try to do. It doesn't work all the time, but if you plan properly, if you know how these intermolecular interactions behave in a complex situation, then you will be able to actually have a good success, fair amount of success. So that is what I will now try to show you. So this is called crystal engineering, and as you already know, once you design the crystal structure, once you control it and get it the way you want, maybe you will also be able to design and control the properties. So that is where is our interest. If you can control the properties, so then this crystal engineering can be very, very useful. So there are a couple of books on the crystal engineering, and Gautam Desiraju is a pioneer in this field. He was at the University of Hyderabad for 30 years, and then later on he moved to IISc Bangalore. So there are books. So there is also textbook. It is written in a very, very simple language, and so you can also take a look at some of these books. So I am sure all of you know that there are different types of intermolecular interactions, right? There are ion dipole interaction. Suppose if you have an ion, so then you have a dipole, like OH bond, for example, is a dipole. There is a fixed dipole, permanent dipole on the polar bonds. So they can interact with the ion. So that is called ion dipole interaction. There are hydrogen bonding interactions. There are dipole-dipole interactions, and there are ion-induced dipole interaction, dipole-induced, and then dispersion interaction means van der Waals interaction. So there are many types of intermolecular interactions, right? So these we can use for designing the crystals. If you know how these work, if you know how which functional group is going to interact with which functional group, if you know these complementary functional groups, then you will be able to design crystal structures. So that is what we try to first understand. First thing is to understand how these intermolecular interactions understand and what is preferred with what. Once you know this, then you will be able to design the crystals. So there is something called supramolecular synthon. Okay. So what is it? For example, if you take carboxylic acid. So I'm sure all of you know what is a carboxylic acid. So you have basically a carbon with C double bond O, and then on the other side you have OH group, right? If you have it, so then here you have a CO group, and when you bring two carboxylic acid groups, so they form a nice dimer, right? You have a CO on one side, on the other side you have OH group, and then they nicely interact in a complementary manner, and then you have two hydrogen bonding interactions between these, between two carboxylic acid groups. So it forms a nice dimer. So this unit is called supramolecular synthon. Okay, once you know that this unit is a very strong one, whenever you have carboxylic acid groups and these molecules come together and then form carboxylic acid dimer. So this is one information that we have, right? So if this is the behavior, and there are many other supramolecular synthons. There are also pyridine to carboxylic acid, amide to amide, amide to carboxylic acid. So there are many other possible synthons. I'm not going to discuss all of them. And there are also close packing. For example, if you don't have any hydrogen bonding group, simply molecules will close pack, right? For example, if you take benzene rings, right? So they will close pack using the pi stacking interactions, right? If you take simple sulfur, right? Sulfur does not have, it's a very bonding based intermolecular interaction. Other one is simple close packing, where van der Waals interaction is the main crucial one. So now we start with this, and then we see how we can actually design crystal structure. So let us start with a carboxylic acid group and see how we can design crystal structure. Right, this is the carboxylic acid. If you have two of them, they will form a nice dimer, and I will show it with this simple cartoon. Right, we will show it with this cartoon. That means that is a carboxylic acid dimer. So now if I introduce it, one carboxylic acid group and a benzene ring. So now I take a benzene ring and then put a carboxylic acid group on it, and then I allow these two benzoic acids, these groups to two molecules to come together and then form a crystal. So what am I going to expect? So I have basically a molecule, and then I put two carboxylic acid groups on it, and then I allow them to crystallize. So as we know, this carboxylic acid group is going to form a dimer, and then they will all come together and then form these dimers. So in the crystal structure, what kind of packing we are going to observe? Any guess? So you have a molecule with carboxylic acid group here and here. I bring all these molecules and then I allow them to form the dimer. Right? What am I going to get? How the crystal structure will look like? So all these linear chains will be there in the crystal structure, right? As you can see here, all the molecules will actually come together and form this dimer, right? They form the dimer, and you get a linear chain, right? Linear chain of molecules in the crystal structure. But if I introduce the carboxylic acid group in a different position, right? In a meta position, so what am I going to get again? So now dimer will be common, because once you have carboxylic acid group, it is going to form a dimer. And then now you should get will you get a linear structure? We are not going to get a linear structure, so it will be rather something like this, right? So depending on the position, you will be able to change the crystal structure. If you take all of them in a linear fashion, you are going to get a linear chains in the crystal structure. Once you have formed this linear chain, they will have to pack in the crystal structure. That may be slightly different depending on what molecule you take, but what is common is you are going to get these linear chains, right? But if you take a meta substitution, and then you get a zigzag tape. But now if I introduce three of them, okay, if I take three of them, what am I going to now get? So each one will behave the same way, because this is one of the strongest interactions, and this molecule has no better other choice, so they are all going to form these dimers. So now when you take these three groups, so then you are going to get something like that, right? You get a hexagonal packing. So then these molecules, it will keep growing, right? You also get these groups here, then another molecule will come, then you can go on getting these hexagonal shapes, right? You get a hexagonal packing, right? So then from these hexagonal, then they will have to stack in the crystal structure, and then if you take this kind of molecule with three carboxylic acid group, then you are going to get a structure where you see these hexagons, and then these hexagons are going to either stack or they can also interpenetrate to close the void, right? That is what you see when you take this kind of molecule. So this is how we design the molecules in our lab, and then we try to control the properties of the molecule. So this is nothing but called crystal engineering. So that is what we do in our lab. So for example, instead of taking carboxylic acid group, on this side I take a alkyl group. Okay, I take an alkyl group and then allow it to do the same thing. So now what happens is, these alkyl groups are basically very weak, so they come in close pack because nobody wants them. So these alkyl groups come together and then they form a basically close packed layer in the crystal. For example, if I have a crystal and then in one layer I have only these van der Waals groups. Okay, so for example, if I have a crystal where I take two carboxylic acid group and form these linear chains, and in the other case I take one methyl, one carboxylic acid and then form structure where I have similar kind of linear tapes, but here I have only weak interactions between these methyl groups. So mechanically, which one will be stiffer? With both carboxylic acids or one carboxylic acid, one methyl? Which one will be softer otherwise? Hope I made it clear. In one case, I have carboxylic acid groups here. It is a nice linear tape. In the other case, I have van der Waals groups, very weak interactions here. So now I take these crystals and then try to break them. Which one will be softer? The one with the methyl groups, because here this layer is very weak. If I had carboxylic acid groups, this would have been much stiffer. So this is how we actually design the mechanical properties. Now you can see, by doing this, you will be able to control the mechanical properties of the material. Right? So, and then this we actually did, and then we shown that these crystals are much softer compared to the examples where you have all hydrogen bonds. And then this is how we could prove that crystal engineering can be actually used to control the mechanical properties of materials. For example, if you have a pharmaceutical solid, and then when you compress, it is so stiff, the particles are so stiff that you can't make a tablet. Right? For example, you take sand, you make very nice powder and then make a tablet. Can you make a tablet? Because particles are so stiff, you cannot make a tablet. But if you take a material which can nicely deform and then particles can stick to each other, if it is soft material, you can make a tablet. So some pharmaceutical solids are very stiff, you cannot make good tablets. So if you can make them little softer, you will be able to actually make them better tablets with them. So this is where we use solid state chemistry techniques like co-crystallization. You take a compound where you have a methyl group, okay, then you try to complex with your API, then your crystals can be much softer. So this is how we can use crystal engineering to design the material. So here we have basically taken a naphthalene diimide moiety, and then we introduced 2 methyl groups, and then we allowed them to crystallize. They form nice pi stacks and then weak interactions here. So then this actually leads to slip planes, and then that leads to basically a very soft crystal. So with this I close here the first talk. And so crystals are everywhere around us, right? These are everywhere. Normally we don't recognize them as crystals. Crystals can be engineered using molecular design principles, right? Crystals can be used for building new technologies. We can also use them for different types of applications. And advanced molecular level studies can help us using crystals for solving real life problems in industries. So if you know how to use this crystal engineering, so you may actually be able to solve some real life problems or design materials for some interesting applications. So with this I close my talk, and thank you very much for your patience.
Thank you, sir, for showing us the beautiful world of crystals. We are in fact running behind the schedule. However, we can have a couple of questions. Please.
Yes, please. Are we late little bit?
First of all, thank you, sir, for your wonderful class. My name is Akhila MJ. My question is, you mentioned about the packing polymorphism here.
Yes, yes.
Does this packing polymorphism always lead to a color change for a crystal?
It can lead to color changes sometime.
If the same crystal shows a different color for some reason, and the packing is different, does we can say that it due to the packing polymorphism that lead to a color polymorphism or not?
Okay, see, if it is the same crystal, you take one piece of crystal and then you put it under different conditions. For example, if you heat it or you put it in some solvent environment or under light, yes. If it is changing color. Yes. So maybe if there is no chemical reaction, you can say it is converting from one polymorphic form to the other polymorphic form. Okay. But if you keep it under light, you are probably making a different molecule sometime. Okay. So it is a chemical reaction which is leading to different molecule that is allowing you to have the change. But if there is no chemical change, you can say one polymorph is converting into another polymorph. Most of the time what happens is molecules may tilt a little bit, or the intermolecular interactions may change a little bit. That can lead to change in these orbital levels, the overlap levels. Homo-LUMO gaps can be changed very easily with the change in the packing. That can lead to the color changes. So okay, you can sir. Definitely
say... So if there is no degradation or anything happen to
no
that...
chemical reaction yes. is happening. Yes.
If no chemical reaction is happening, that we can conclude
you
that...
You can conclude as a polymorphism.
Yes.
Packing polymorphism, if the structure is very similar, then there is again subclassification: packing polymorphism, synthan polymorphism, conformational polymorphism. If you see two polymorphs with different conformation of the molecule, you call it as a conformational polymorphism. If the packing, what I have shown was an example of a packing polymorphism. In one case, all the molecules are like this. In the other case, some are like this, some are like that. So the packing is different. So that can be called as packing polymorphism. So there are different versions of polymorphism, but you have to look at the structure to decide which type of polymorphism it is.
Okay, so further, if any reaction is not happening, that packing maybe we can explain the color change for the crystal with the help of this packing polymorphism.
Yes,
okay,
based on the polymorphism.
Okay,
yes.
thank you, sir.
Yeah. Okay.
More questions?
Yes.
And the relation with the crystal formation, right?
Right, right.
Is it like the percentage of cocoa butter that we add also affects the melting? Is it
Yes.
any
See,
relation?
if you make a composite, both the components will play a role in the melting. But if given all the conditions, other conditions are same, only the variation is polymorph. So you will see this different. But if you take pure cocoa butter, the melting points which I have shown will match. Yeah.
Okay. On behalf of everyone gathered here, I would like to thank Professor Reddy for the insightful and inspiring talk. Thank you.
Thank you very much.
The meeting is now adjourned for a short break. Refreshments have been arranged at the Marine Hall. All are requested to muster by 10:45 for the next session. A gentle reminder, attendance sheets have been available outside the hall. Participants, please do make sure to mark your attendance. Oral presentations on general chemistry and wastewater treatment will be starting by 11:30. Thank you.
And recently we also had a special issue, and this topic is becoming very popular. As you can see, number of publications in this area are growing with time, and so then citations to these papers are also going. So in this special issue, myself and Calvin Sun from University of Minnesota, we wanted to understand how this field is growing. So we did a simple survey, and then we found that the number of studies on mechanical properties are actually growing. There are only small number of groups working on the mechanical properties of crystals, and one of the early groups to start the work on mechanical properties is ours. So as you know, normally organic crystals or any type of crystal means we assume that they are all very fragile, right? So if you take any crystal, if you apply mechanical stress, normally we assume that they break, right? Most of the crystals, organic crystals, normally break when you apply the mechanical stress. So this is very common, and if you look at the crystals and liquids, and there are some crystals which are actually crystalline materials which are also softer little bit. So how do we understand all these in one umbrella, under one umbrella, and then how do we rationalize these properties? For example, as we all know, liquids have the flowability, right? They nicely flow. And if you look at the order, internal order, there is no order. Right? It's very uniform, and then you have isotropic environment normally for the liquids, and then there is a lot of mobility. There is no crystalline order in case of proper liquids. But if you go to, so if you put them under this plot, so this is order. So if the order is more and more, so then if you go to this highest order where molecular motion is very less here, so you have crystals here, and then you have liquids on this side. So this is how you can basically put them on a molecular mobility versus order plot, right? So here you have liquids, and then you have proper crystals where inside molecules, in the crystals molecules have actually the highest possible order, and molecules are also static mostly except the vibrational motions. So molecules don't have normally any other motion. So if you look at these, they are normally very brittle, and all the molecules are frozen normally except the thermal vibrations. So you cannot really do anything with these, and then if you apply any stress, so they can simply break down, right? That is what we assume. So but there are some interesting class of molecular crystals or class of crystalline materials in between these two states. For example, if you look at, I am sure all of you know about the liquid crystals, right? So in liquid crystals there is some kind of order, okay? All the molecules have some kind of order, but at the same time keeping that order intact, molecules can actually together move and flow. So that is what is called liquid crystalline state. You have some level of order, but it may not be as good. Normally it is not as good as what you have in the ordered crystals, right? Proper single crystals. So there is some kind of a orderness, and there is also some kind of a liquid-like behavior. So these are called liquid crystals. So we have these in the computer displays and many places, right? LCD. What is LCD? Liquid crystal display. So inside you have these liquid crystals. So this is a combination of liquids as well as the crystals. So there are other materials where you have plastic crystalline material. So here the crystal is highly ordered, and molecules don't move from their position. There is no flow here. But what happens is each molecule in its own position, it can rotate. Okay, it will not move anywhere. You have nice order. The center of mass of this molecule is always in one place, but the molecules can actually rotate in the solid state. So these are called plastic crystalline phases. So why do you call them plastic? Because these materials are very, very soft normally. If you apply mechanical stress, so they deform very easily. They don't break like other crystals, so they are very soft. That is why you call this as plastic crystal. There are some crystals which are called amphidynamic crystals. So here again molecules are kind of static, but one part of the molecule may actually rotate. For example, a methyl group in the molecule may rotate. Rest of the molecule is actually intact, but only some portion of the molecule is rotating. So those are called amphidynamic crystals. Okay, maybe if you have a big molecule, in the middle you have a benzene ring. That benzene ring can actually rotate. Only some components of the molecules rotate. If you have that kind of a crystal where order is very good, the molecules have very good order, but only one components rotate, and those are called amphidynamic crystals. So in liquid crystals you have some order, but molecules can completely move. In plastic crystals, molecules cannot have translational motion, but each molecule can rotate in its own position. Entire molecule rotates in its own position in plastic crystals. In amphidynamic crystals, only part of the molecule rotates, but otherwise it is a very nice crystalline material. So there are some other material where if you apply the stress, otherwise they are normally static molecules. Molecules are frozen kind of, but if you apply the stress, molecules can rotate, move with respect to each other. So these are called soft crystals, and our group mainly works on this, and I'll show you some examples. Only when you apply the mechanical stress, molecules actually will move, and sometimes they can come back to the original position. Those are called elastic crystals, and sometimes they cannot come back to the original position. They are called plastically deformable crystals. So plastic means normally the irreversible deformation. In the mechanical engineering terms, plastic deformation means the deformation is not reversible. So once you break it or once you bend it, for example, if you take a copper wire and you bend it, right, it will not come back. It will remain in that position. So that is called plastic deformation. Elastic means you bend it and then release the stress, it will again come back to normal position. So that is called elastic deformation. And so mechanical deformation in molecular crystals is very, very important in many, many areas. Mechanical properties are important. For example, if you go to flexible electronics, mechanical properties are very important, right? For example, organic crystals, like if you want to design a skin-like material with the thin films, so if your crystals are not flexible, then although you make a material or a patch which is flexible, substrate may be flexible, but your crystal may not be flexible, that can lead to problems. Or in pharmaceutical industry, when you are making when you make molecules in quintals using synthetic chemistry, then you have to take it into market. So you have to put these APIs under a lot of stress, at different conditions to make a tablet or to reduce the particle size, while flowing, while mixing. In many places, you need to put pharmaceutical solids under mechanical stress. So in all these aspects, so it becomes very important to understand how crystals behave under mechanical stress. So that is what I will try to show you. So, and these soft crystals can have many applications, like now there is a lot of interest on robotics, right? So there is soft robotics, particularly where people want to use materials which are very soft but respond to some kind of a stimuli. There are a lot of polymeric and elastomeric materials in use right now. People are working, but crystals are still not into too much of exploration, but eventually I feel that even molecular crystals will also be explored by people. So if you want to classify the molecular crystals based on the response to the mechanical stress, so we can say that crystals can break when you apply the stress. This is very usual. If you take any crystal, apply the mechanical stress, so they will break. So this is very common, and these are called brittle crystals. And crystals can also bend elastically, and once you release the stress, right, as you can see, this is a single crystal, this is a single co-crystal of a caffeine, right? The caffeine is the main ingredient in the coffee, right? If you take these molecules and co-crystallize with one of the benzoic acid derivatives, so you get a co-crystal. Co-crystal means in the unit cell you have a caffeine as well as some other molecule like a hydrogen bonded together, and that forms a crystal which is called co-crystal, because two components crystallize together to give you a neutral crystal, right? So this is an elastic crystal. When you bend, so it may bend, and then once you release the stress, it will come back, right? This is called elastic deformation. And then crystals can also deform irreversibly, as you can see in this case. So this is a very simple molecule, crystals of a simple molecule. So the molecule here was actually hexachlorobenzene. Okay, if you take hexachlorobenzene, crystallize it, you get these nice crystals, and then you take them under a microscope, take a forceps, and then and then push it with a needle. Then you see that they bend very nicely like this. So this is a hexachlorobenzene crystal. It bends and then it doesn't come back, but here it bends and it comes back. So what is the reason for this? So can we explain this behavior by looking at the crystal structure, right? Can we design them? If we can design, then what will be the uses, right? and then this is what can be done using crystal engineering principles, right? So you have a brittle crystal. This is normal. Most of the crystals are brittle. If you take any crystal, bend it, so they break like this. These are very fragile organic crystals. So then there can be some small section of crystals which are elastic, which are recoverable, and there are some crystals which break, which bend permanently. So these are called plastically deformable crystals. So these are the main three different types based on the response to mechanical stress. So let us look at plastically deformable crystals and then see why they actually bend plastically. So what do we need to do? We have to look at the crystal structure, right? So we did a detailed investigation. I am not going into the details of this. If you look at the crystal structure, so these hexachlorobenzene molecules stack one over the other. As you can see here, this is a disc, and then below that there is another disc, another disc. So they pack like this, like discs. Okay, these discs are actually parallel to each other. And the needle direction, this is when you look at the crystal, so crystal is like this. If you look at inside, the molecules are packed like that. Okay, so, and it is somewhat like this. And so when you have these stacks, between these stacks you have only weak interactions. Okay, these chloro-chloro interactions are very weak. So you can move these stacks one, parallel to each other. For example, if you take A4 sheets, you can bend nicely like this, right? So because sheets can roll one over the other, and then you can nicely bend. So that is what happens exactly here, and that is why these crystals bend. So it is a plastic deformation, right? So this, we took many molecules and then we have basically introduced the weak interactions, and we got this packing. You have stacks with methyl-methyl weak interactions here, and when you basically take these long crystals where you have packing like this, and you have weak interaction planes parallel to the needle axis, like these sheets. So then once you bend it, so they nicely bend, right? As you can see here, you can see this edge here. It was, this angle here was 90 degree between this face and this face. But now, as you can see here, this is not 90 anymore. It is more like what you see in this paper, these yellow, sticky papers, right? If you bend it, it become like that. So the mechanism is exactly like that. So you have weak interactions through which molecular layers can actually move. So that is the mechanism. And by looking at the crystal structure and orientation of the packing inside, so you should be able to explain the physical properties of the crystal. So that is what we did, and we did it for many molecules, and then we have shown that it is possible to design these plastically deformable crystals. Okay, this is the first example where we showed that it is possible to design. So then Professor Chandrasekhar from University of Hyderabad has used these many mechanically bendable crystals, and then their crystals are luminescent crystals, and apart from the luminescence, they can also mechanically bend. So they took them, and using an AFM tip, they took very small crystals, and then they made many circuits like this. Then you shine light from here, and the light actually travels to the crystal, and then it propagates in different ways. So they made these kind of photonic circuits using these mechanically deformable crystals. Okay, so this could have future applications, and their group nicely demonstrated the use of these mechanically deformable crystals. So there are many attempts by other groups to use different types of materials for different types of small robots. For example, if you see his group, he is from Max Planck University from Germany. So their group has been using these small robots. So they have basically, these strips. So depending on the light intensity, so they can basically swim like this. So you can make, as you can see, just you keep shining the light, and then it will keep doing like this. So once you shine the light, these basically strips bend. Okay, in response, mechanically bend. Using that motion, you can actually design some of these. As you can see here, if you shine light, there is a bending. So in a controlled way, you keep shining the light, then it bends. Then on this track, it can nicely walk. So these kind of things can be done with the mechanically deformable crystals, and people have been using certain crystals to show the practical utility. So initially, our group showed that crystals can be bent, and there could be plastic and elastic crystals. So this was done from our group first. Then after that, many people all over the world have found similar type of crystals with different interesting properties. For example, if you see here, this is an elastic crystal from a Japanese group. It is also fluorescent, elastic as well as fluorescent, and they have shown this video under UV light, and you can see nicely it bends. And this is from a Chinese group, so you can twist the crystal as well as you can also bend it. And here this is a inorganic complex from Mariana Dakovic, and so you can also see this is a metal organic complex. Okay, so coordination complex. It's not a coordination. It's not a morph, but it is a coordination network. I think maybe one-dimensional network. And this is also another coordination complex. So you can also see plastic deformation, elastic deformation. This is a jumping. Okay, crystals can also jump when you heat it. So when you heat, what happens is the crystals convert from one polymorph to the other polymorph. So when it happens, the unit cell dimensions change a little bit. So since the phase transition happening very quickly, so when you heat them up to one temperature, the stress will keep building up. But when you reach that phase transformation temperature, suddenly the unit cell changes. The whole material changes the shape suddenly, then that leads to this mechanical jumping, as you can see in these two crystals. Okay, so then there are many examples, and a lot of interesting things have been shown. This is from our group. If you shine the light, there is a polymerization reaction on the surface. So there is a polymerization reaction on the surface when you shine the light from here. So because of the polymerization, the unit cells here become shorter, and that is why the crystal actually bends like this. Okay, because once unit cells on this surface are shorter, so then crystal will bend like this. So this is also an elastically deformable crystal, and because of that you will be able to see that kind of interesting property. So then there are other interesting examples, like you can see here, you can stretch the crystal, still it remains highly crystalline, and you can also compress it. You can basically also put two crystals together, compress them, they nicely stick, almost like self-healing. So you can go on doing a lot of things, and so in all these cases we have a very clear-cut explanation from the crystal structure. I am not giving you all the details here. So everything can be explained using the crystal structure. Whatever you see in crystals, if you do careful experiments, if you understand crystal structure properly, if you know how these molecular interactions play a role, so then you will be able to explain them, and then eventually that will allow you to also design such crystals which can be useful for different types of applications. Right, in this particular case, molecules actually rotate in the solid state. Once the molecules start rotating, these are more like globular molecules. So they can more like metals, like even copper, if you see all the metals are spherical, right? So here these molecules are also spherical in nature and almost like a sphere, and these molecules can rotate, and once they start rotating, the interactions also become very weak around it. That is why you will be able to slide them in any direction you want, like what you can do in metals. So that is why it behaves almost like a metallic material. So then I will talk about the self-healing. Self-healing is very common in nature. For example, if you break your bone, so right after 2 months you see that fracture is actually healed, right? So generally what happens here in the bone, when you have a crack, so since it is a composite, there is a collagen as well inside the bone, so it develops some kind of a surface charges. Because of these surface charges, so this comes from the piezoelectric nature of this material. So because of the surface charges, then some cells come here and then they heal they deposit the minerals there, and then that is how healing happens in case of bone. Okay, this is in the nature, and there are also other examples. For example, if you take a polymer here, it's a soft gel. So here you have a polymer network, and then there are also side chains which have a lot of hydrogen bonding groups. And in the polymer network, you also have a lot of solvent. Because of this, when you cut this and then put the two pieces together, so these side chains move freely, and since there is also a lot of solvent, movement is very easy, diffusion is very easy, then they entangle at the surface, and then that is how you see the self-healing here. As you can see here, you take this polymer gel, you cut it, and with time you see that the gap is actually gone. So this is another mechanism. There are different types of mechanisms. As you can also see here, you take these soft gels, put it in this buffer solution and cut and then put them together, and you can clearly see that there is a nice self-healing in these crystals. Right? There are different. These are gels basically. They are not crystals. So most of the examples which are reported in the literature are from the soft gels, or from the soft polymers, or from the soft elastomers. And in crystalline materials, hard materials, there are hardly any reports. So now there are a few, but when we came across this particular example, as you can see, this is a very simple material. Many times this is used by inorganic chemists as a ligand to complex with metals. And we were working with this, and my student Surajit found that when you apply the mechanical stress, so a crack develops, but once you release the crack up, automatically the crystals actually close the gap, as you can see here. So if you push it, there's a crack, then there is nothing almost. So it completely heals and you don't see anything, and you don't have to put these crystals together. They come back on their own, right? So then we were very much puzzled because there was no such report in the literature. As you can see here, a big crack comes out, and then once you release the stress, this is basically a forceps, and then you have a needle, you push the crystal. If your crystal is like this, you push from this side, you generate a crack. Once you release, it automatically goes back. Then we were wondering what exactly is happening here, why they are coming together, what is allowing it to come together. Then we found that when you basically allow these crystals to stay closer, as you can see in this case, you break the crystal and then push this closer to this, and then you see that there is a lot of attractive force. So the crystal basically jumps and then it gets attracted to the other part. So as you can see, there is an attraction. So then it's not a magnetic material because this is a simple organic material, and there is also no radical. So we were wondering what is leading to this attraction. So then we did all the analysis, and we found that these crystals are actually piezoelectric. So any piezoelectric material, so if it is a piezoelectric material, so normally all the dipoles are neutralized in the pristine state, but once you apply the stress, uniform stress, you are basically distorting these dipoles. Because of this, on one side you may have positive charge, on the other side negative charge on the crystals. Okay, when you have positive and negative charge because of the piezoelectric nature, and then you can have these surface charges on the broken material, and then that can lead to this attraction. So that is what we found, and then we wanted to prove that there is a charge here using some experiments. We do these. We took a crystal, we broke it, and then put them together again, and the crack was, still there because the healing was not perfect. And then we measured the charges using Kelvin probe force microscopy, and then when you measure it, on one side we see negative charge, on the other side we see positive charge. This tells that there are actually surface charges, and because this is a piezoelectric crystal and you have surface charges, and that leads to this attraction. So that we could explain from that. So using all these experiments, we could basically give a mechanism. If you take this crystal, so if you take these crystals, since it is a polar space group, all the dipoles are arranged in one direction. So if you cut it, so one side, on one surface you will have heads, and in the other side you will have tails. So because of that, on one side you have positive charge, on the other side you have negative charge. And because of this, these crystals actually get attracted when you basically, when you mechanically deform them. That is the mechanism we have given. As you can see, all the dipoles are arranged in one direction. If you break it, one side you have negative charge, and the other side you have positive charge. That allows the crystals to heal. So, and when we published this, then some journalist called me, and they wanted a story on this. Then I gave it. Then I didn't realize that they are going to put it on the front page in Telegraph. And then in the morning I started getting a lot of calls. Then I realized that they have put it on the front page. Then I called the journalist and asked him, normally you put these kind of things in a last page somewhere in a small corner. So what made you to put it on the front page? Normally you will see either in Bengal, Mamata Banerjee or Modi or somebody else. So then he told that so this was published in Science, completely from Indian group. So then he said that our editor-in-chief was very impressed to see these videos. So then he said, let's put it in the front page. And I said, okay, you also respect scientists sometimes. So I was very happy. So, and so then we published it in this paper here. You can read the details and you will find it. And so with this I conclude, self-healing in molecular crystals is possible to design. Now we have many experiments. So we are finding ways to actually design the self-healing crystals. For example, if you have a self-healing semiconducting crystal, you can use it in the devices. If you have a self-healing second harmonic generation crystal or optical crystal, you will be able to use it in many devices. Okay, if you want to use a crystal as an actuator in a micro robot, for example, and if it is also self-healing, so it can be also very useful. So we are now designing self-healing crystals with an additional property so that we can use it in different applications. So that is what we are currently doing, but I'm not going to show all those results today. And with this, I conclude my talk. Thank you very much. Okay, I hope I save some time.
Thank you, sir. Now we have interactive session. I hope this lecture might have sparked new ideas and curiosity among young minds. So I expect more questions this time. Yes.
Hi sir, myself Shilpa. Sir, my question is, the size of atoms, does it affecting the mechanical bending property? Does it affect the mechanical bending property of crystals? Atom size?
See, we are working with molecular crystals. Okay, we are not working with atoms. So it is not the size, it is the, for example, particularly for the self-healing crystals, what is more important is the crystal system. So there, the unit cell should have a net dipole moment in one direction. For example, if this is your crystal, so when you have unit cells in this direction, so unit cells should have a net dipole moment in this direction. So if all the unit cells are aligned in this direction with a dipole moment in one direction, so you have positive charge here and negative charge here for all the unit cells. When you cut it, so then one side you have heads, other side you have tails. So that leads to the attraction. So crystallographic details are much more important than any other factors in case of self-healing crystals. But in case of elastic and plastically deformable crystals, again intermolecular interactions, these weak interaction planes, some of those play a crucial role. But not exactly the size of the molecule or atom.
Okay sir, thank you.
Good morning, sir. This is a small doubt. I have a kid, and he used to play with a ball, and that ball is very soft. When we hit the ball on the wall, it will stick on there, and when it after some time, it will come back as the ball itself. So, is it an example of elastically deformable crystal?
If it is recovering completely, yes.
Yes.
But it may be elastoplastic. There is something called viscoelastic materials. If you hit it, then it stays in that deformed state for some time, but eventually it will actually recover. So these are called viscoelastic materials.
Okay.
So they have both elastic-like and plastic-like behavior. It's a mix of the two properties. It deforms, but then eventually with time, there is a time factor here. With time they recover. So these are more like viscoelastic materials. So but they recover also fully. So there is a time-dependent response in those kind of materials.
Okay. Thank you.
We have enough time for more questions.
I think maybe I was a little too fast.
Don't hesitate.
Sir, is there any criteria for designing the molecule which will show this property?
You mean elastic property or?
Elastic property.
Elastic property. See, generally we found that if your molecule is it's not strictly needed, but if you have a flat molecule, for example, so then if these are stacked, if they have aromatic rings, for example, if you have a flat molecule, so they stack nicely. So when these molecules stack like a herringbone with a herringbone packing like this, so you will be able to move them like this. Okay. For example, if you have a crystal like this, so on the outer surface, when I take a crystal and then bend it like this, so when I make a curve, so on the outer side I have to stretch it, on the inner side I have to compress. Okay. So if you have molecules which are like this, for example, pack like this and like this. Suppose if I have a unit cell on the upper side, for example, I have a crystal. So my molecules are basically stacked. There is one stack here and one stack. So if I have to stretch it, so if I have to stretch the unit cell, so if I do like this, okay, this from here to here, if it is like this, okay, if I move it like this, right, if you are able to move this is I am able to stretch when I do this, and I am able to compress. On the inner side there is a compression, they move like this. On the outer side they do like this. So once they start moving like this, whenever you have these flat molecules which stack like columns, with the corrugated columns, so you will be able to bend them. So for designing elastic crystals, so that works very well. But there are other systems which also show this to some extent, but you get easily the elasticity when you have these stacked molecules which pack like these corrugated sheets. So that is a good way. And generally also, if you have weak interactions, it works much better because it is easier to deform the molecules in interactions. But when you have very high strong interactions, then moving the molecules in the crystal structure becomes little difficult. Okay, and if you have defects also, then that will also lead to fracture. So crystal quality should be very high, and then you should have certain packing which will allow this expansion on the outside and then compression on the inside. So if that happens, then it is possible to bend the crystals.
Sir, but that we'll get after doing the crystal studies.
You need to know which kind of molecules will be able to pack in that particular way. Normally, if you have a aromatic molecule which can pack like stacks, they give you this property.
Thank you, sir.
I don't know whether this is an apt question. Actually, now from the animal samples, the protein crystallography is doing by these engineers particularly. My question is any reverse type. Nowadays, using the AI tools, now the protein structure prediction is going on.
Right.
So if any unknown proteins are there, and by any sequence, if the correct structure of the protein is predicted by using any AI tool, we can make such proteins, whether it is possible to crystallize. Nowadays, from the animal samples, they extract the protein part and they crystallize it.
Right.
Any reverse process is developed?
I think it is, for crystals, we work with small molecule crystals. We don't work with protein crystals. Okay. So what you are asking is, if you know the crystal packing, maybe you can predict in a reverse direction and see if some crystal which is already known, but the property is not known. Whether you can predict using the crystal structure using AI tools and other things, right? That is what you are asking. So it is possible, and but right now there are no systematic studies on that. So we attempted in collaboration.
No, my question is if any amino acids are missing.
Okay.
That means a partial sequence is known. The full structure of the protein is not known.
Okay.
But by any AI tool, if we get the complete sequence, we can
now people are doing
the fragments.
People are doing those kind of studies, and already there is a good success in some cases.
Okay.
So like with more and more tools, definitely it is going to become much more feasible in future. Yeah, people have been doing that because proteins, the variation is not so much.
Okay.
Right, because all of these are amino acids with small changes.
Exactly.
So when you look at a conformation also, most of them behave in a very predictable manner.
Actually, this novel work is the full protein structure prediction. It's too much, more than 75% matching with the experimental studies from the AI tools. So that is why reverse.
But with molecular crystals, it is much more difficult because each molecule is so different from other molecule, and there is no. You are talking about the intermolecular arrangement, but in case of protein, it is more about the intramolecular where molecules are connected with covalent connections, right? So there it becomes much more straightforward. But in case of small molecules, how each molecule will pack in a 3-dimension is much more complex. So that is why it is not so straightforward in case of molecular crystals.
Thank you, sir.
There is one. There, lost.
Hi sir, I am Femina. I'm working in pi conjugated organic compounds. So most of the organic compounds, we are actually looking forward the formation of crystals. So most of the compounds are difficult to form the crystals. So I'm asking, is there any easy method to form to grow crystals?
So first of all, you need to have a pure compound.
Okay, sir.
Okay, once you have highly pure compound, and I guess your compounds are also not easily soluble.
Yes, some compounds are soluble, even though we get 2 or 3 crystals, but some compounds very difficult. If we try in any solvent, it is very difficult to form.
Sublimation could be also tried actually.
Yeah, we
Sublimation.
are looking slow evaporation method. We are trying.
But if you are trying slow evaporation method, normally you take dilute solution and leave it for long time.
Okay.
So maybe that will help. Sometime in NMR tube or small narrow test tube.
Yeah.
You take lot of solvent. You can also use layering method. You dissolve it nicely and then on top of that you put a layer which is lighter in terms of density and also going to stay there. So then there will be a small diffusion that can also give you better crystals. So there are different crystallization techniques which you can try. But
Okay,
sometimes nothing works.
Thank you, sir.
We can have just one more question.
Hello, sir. As you have shown that the crystals get self-filled, can you tell me what type of interaction present in the crystal that leads to the self-filling?
Okay, it's a good question. So it is not about the interactions. Initially we thought interactions are playing a role, but as I said, it is about the unit cell dipoles. For example, if you have a unit cell, we have now some examples where there is no hydrogen bond at all. Okay, these are very simple molecules, and even but there is a dipole, net dipole moment for the unit cell. For example, you have a crystal, you have unit cells in this direction. So unit cell has a net dipole moment in particular direction. So when you break the crystal perpendicular to that, then you have head to tail arrangement. So that leads to self-healing. So you need particular space groups. So crystal symmetry should be such that you have all dipoles aligned in one direction. So in those cases, there is a good possibility of getting the self-heal.
Okay, sir. Thank you.
Okay, if you have more questions, you can interact with him during lunch break. Once again, thank you, Professor Reddy, for sharing with us your expertise, and we hope to see more of your groundbreaking work in the near future.
Thank you.
Let us show our appreciation with a big round of applause. Thank you.
Thank you, Dr. Reddy, for this presentation, and Dr. Sindhu Mathai for presiding over the session. As a token of love, we would like to present a memento to Dr. Reddy and Dr. Sindhu Mathai. I request Dr. Sindhu Mathai to present the memento to Professor C. Malareddy. And I invite Dr. Grace Thomas, Associate Professor, Sacred Heart College, to give away the memento to Dr. Sindhu Mathai. Thank you. Now, we move on to the oral presentations on the themes General Chemistry, followed by Wastewater Treatment, after which lunch would be provided. All are requested to assemble for the plenary lecture 4 by Professor Kana M. Sureshan by 1:30. Thank you.
It will stand. It will stand. Okay, we got a chance to participate in the 23rd K.V. Thomas Fund Endowment Award National Seminar, which is organized by the Department of Chemistry, Sacred Heart College, Thevara. In this session, we got so many plenary lectures which will be more informative to research scholars, and having interactive sessions with a novel scientists from the different parts of our country. And once again, I thank to Department of Chemistry for organizing this seminar and giving a chance to interact with the eminent faculties and scientists from the various.
ഞാൻ കെമിസ്ട്രി ഡിപ്പാർട്ട്മെൻറ്റിലെ തേർഡ് ഇയർ സ്റ്റുഡൻ്റാണ്. അപ്പോൾ KV തോമസിൻ്റെ 23rd സെമിനാറാണ് ഇപ്പോൾ SH നടക്കുന്നത്. ആസ് എ പാർട്ട് ഓഫ് കെമിസ്ട്രി ഡിപ്പാർട്ട്മെൻറ്റ് സ്റ്റുഡൻറ്റ് എനിക്കിത് ഭയങ്കര അഭിമാനമുള്ളൊരു നിമിഷം തന്നെയാണ്. ഒരുപാട് സയൻറ്റിസ്റ്റുകൾ കോളേജിൽ വന്ന് നമ്മുടെ ഡിപ്പാർട്ട്മെൻറ്റിൽ വന്ന് മറ്റു കോളേജിൽ വരുന്ന പിള്ളേരുമായിട്ട് സംസാരിക്കുക, ഇൻട്രാക്ട് ചെയ്യുക. ഞങ്ങൾക്കും ഗുഡ് എക്സ്പീരിയൻസ്, നല്ല സയൻറ്റിസ്റ്റായിട്ട് ഞങ്ങൾക്ക് ഇൻട്രാക്ട് ചെയ്യാൻ പറ്റുന്നു. ഗുഡ് എക്സ്പീരിയൻസ് ആണ്. പാർട്ട് ഓഫ് ദിസ് ഐ ആം വെരി ഹാപ്പി ടു ബി പാർട്ട് ഓഫ് ദിസ്.
23ാമത് KV കുഴപ്പമില്ലല്ലോ, ലൈവാണല്ലോ. 23ാമത് പ്രൊഫസർ KV തോമസ് എൻഡോമെന്റ് നാഷണൽ സെമിനാറിൻ്റെ 2ാമത്തെ ദിവസം നമ്മളിപ്പോൾ വിജയകരമായിട്ട് നടന്നുകൊണ്ടിരിക്കുകയാണ്. രജിസ്ട്രേഷൻ കമ്മിറ്റിയുടെ ചുമതലയാണ് എനിക്ക് ഈ ഓർഗനൈസിങ് ടീം എന്നുള്ള നിലയിലുണ്ടായിരുന്നത്. ഏതാണ്ട് 135ഓളം പ്രതിനിധികൾ കേരളത്തിൻ്റെയും അതുപോലെ തന്നെ ഇന്ത്യയുടെയും വിവിധ യൂണിവേഴ്സിറ്റികളിൽ നിന്നും വിവിധ റിസർച്ച് സ്ഥാപനങ്ങളിൽ നിന്നും വരികയുണ്ടായി. വളരെ നല്ലൊരു അനുഭവമായിരുന്നു. ഇത്രയധികം ആളുകൾ വിവിധ മേഖലകളിൽ ഗവേഷണ പ്രബന്ധങ്ങൾ അവതരിപ്പിക്കുകയും അതോടൊപ്പം തന്നെ അവർക്ക് വളരെ പ്രഗത്ഭരായിട്ടുള്ള ആളുകളുടെ ശാസ്ത്ര പ്രഭാഷണങ്ങൾ കേൾക്കാനും ഒരു അവസരമുണ്ടായി. പുറമേ നിന്ന് വന്ന പ്രതിനിധികൾക്ക് കൂടാതെ നമ്മുടെ കോളേജിലെ വിദ്യാർത്ഥികൾക്കും ഇത് വളരെ നല്ലൊരു അനുഭവമായി എന്ന് കരുതുന്നു. താങ്ക് യു. പോരെ.
23ാമത് KV തോമസ് എൻഡോമെൻറ്റ് സെമിനാറാണിത്. നാഷണൽ സെമിനാറുകളും ഇൻ്റർനാഷണൽ സെമിനാറുകളും വളരെ കുട്ടികൾക്ക് വളരെ പ്രയോജനമാകുന്ന രീതിയിലാണ് ഇത്രയും നാൾ ഞങ്ങൾ നടത്തിക്കൊണ്ടിരുന്നത്. ഈ വർഷം പ്രഗത്ഭരായ സയൻറ്റിസ്റ്റുമാരുടെ ഒരു നിര തന്നെ ഈ ഒരു സെമിനാറിന് റിസോഴ്സ് പേഴ്സൺസ് ആയിട്ടുണ്ടായിരുന്നു. പത്മശ്രീ T. പ്രദീപ്, IIT-യിലെ ഇൻസ്റ്റിറ്റ്യൂട്ട് പ്രൊഫസറായ T. പ്രദീപ് മുതൽ ഐസറിലെ ഖാന സുരേഷൻ വരെയുള്ള വളരെ എനർജറ്റിക് ആൻഡ് റിനൗണ്ട് സയൻറ്റിസ്റ്റുമാരുടെ ഒരു നിരയാണ് എല്ലാ വർഷവും ഞങ്ങൾ കുട്ടികൾക്കായി ഇവിടെ കൊണ്ടുവരുന്നത്. ഇത് ഞങ്ങളുടെ കുട്ടികളുടെയും ആസ് വെൽ ആസ് ഇവിടെ വരുന്ന എല്ലാ വിദ്യാർത്ഥികളുടെയും ഒരു ഭാവിയിൽ വളരെ പ്രയോജനകരമായ ഒരു ബന്ധം ഉണ്ടാക്കാനും ഇപ്പോൾ ഫ്രോണ്ടിയർ ആയിട്ടുള്ള കാര്യങ്ങളെപ്പറ്റി കുട്ടികൾക്ക് കൂടുതൽ അവബോധം ഉണ്ടാക്കാനും
School of Chemical Sciences, Mahatma Gandhi University. Here I am presenting one of my research work entitled with functionalized polyacrylonitrile supporter, copper catalyst for copper acid alkane cycloaddition reaction in water. Click chemistry is one of the most convenient and aesthetic route for the synthesis of a functional molecules from modular building blocks under ambient condition. In 2022, KB Sharpless and Meldal Rheolin or Betroxy share the Nobel Prize for Chemistry in recognitions for an overwhelming embrace of this reaction. Chronology of click chemistry. In 1963, Rolf Hugisons introduced 1,3-dipolar cycloaddition reaction, which is an ideal prototype for illustrating the concept of click chemistry. In 2001, KB Sharpless introduced the term click chemistry. In 2002, KB Sharpless and Meldal independently carried out the research in presences of copper catalyst, and they found that the product obtained with high yield and high ratio selectivity. In 2004, kaolin Betroxy started utilizing click chemistry in living organisms. After 2004 onwards, there are plenty of publications indicating the wide acceptances of this reactions due to its attractive features like modular, wide in scope, inoffensive byproduct, high yield, insensitive to air and water, and simple reaction conditions. Due to these attractive features, it has wide applications in the field of catalysis, polymer sciences, material science, bio and medicinal chemistry. The classic copper acid alkane cycloaddition reaction is usually carried out in homogeneous catalyst, but this catalytic system has some disadvantages, and the researchers started to heterogeneize the homogeneous catalytic systems with the help of various supporters like silica, zeolites, polymer, MOF, and magnetic nanoparticles. Among them, the polymer supporter system receive much more attention due to the use of selectivity. and low cost than other materials. And the first polymer supporter system is the Merrifield resins, and majority of early reports are based on polystyrene basis supports. And by the step-by-step development of this polymer supporters catalysis, the polymer functionalization faces a crucial role for the conversions of a functional group in polymer backbone into a broad range of other functional groups. The chemical modifications of nitrile groups in polyacrylonitrile is an example for this polymer functionalizations, and which were detailed in one of our review papers. And the modified polyacrylonitrile in supported catalysis, the modified polyacrylonitrile polymer can be used as a solid support for the immobilization of transition metals, and this can be achieved through chelation mechanism, and thereby it acts as a heterogeneous catalyst. And the major advantages of this systems includes easy preparation, stable against air and moisture, and can avoid the use of expensive ligands, and moreover the catalyst can be reused for several times. On behalf of this, we have developed a novel heterogeneous polymer supporter metal catalyst for various organic reactions. These are some of the catalytic systems that's in our lab for various coupling reactions, CEH activation, and recently for Fenton processes. So after the successful results of this catalytic system, so our next step is to upgrade the synthetic applications of this catalytic system for the synthesis of a heterocyclic compounds through one-pot reaction. So we thought, why don't we try it in click reactions? For that, we have chosen MPAN copper 2 as a catalytic system. So this is the main objective of my work. After complexation, we check the catalytic activity of this catalyst using click reaction, synthesis and characterizations of MPAN copper. Polyacrylonitrile undergoes synthetic modifications with monoethanolamine and generating an MPAN, and which on complexations giving MPAN copper 2, and it were characterized by using FTIR analysis. The nitrile groups in polyacrylonitrile disappears after the synthetic modifications with monoethanolamine. The EDS analysis reveals the presence of copper in these catalytic systems along with the presence of carbon, nitrogen, oxygen and chlorine, and the ICP-MS analysis also revealed the presence of copper within the amount 14,277.43 ppm of copper in 1 gram of this catalytic system. After all these characterization studies, we check the catalytic efficiency of these systems towards 1,4,3 component reactions of benzyl bromide and phenylacetylene, and the product obtained with the 28% yield, and it were confirmed by using GCMS, and the obtained product were characterized by using H1 NMR and C13 NMR spectra. And after the optimization, after the characterization studies, we go for an optimization. And the first is a solvent screening. Water is an efficient solvent to carry out this reaction. And from the catalyst loading, 20 mole percentage of catalyst is sufficient. And from room temperature optimization, room temperature is an ideal condition to carry out this reaction. But after all this optimization studies, we can increase the yield of the product above 62%. In that times, we introduce sodium ascorbate to this reaction conditions, and the product obtained with the 89% yield. This is optimized conditions for this reaction. After the optimized condition, we check the generality studies using diverse ranges of benzyl bromide and phenylacetylene, and we had done almost 24 examples, and the product obtained with the 63 to 98% yield. Then we proposed a possible mechanism for this catalytic systems, and this is the possible mechanism for this reactions. And then we check the reusability of the catalytic systems in this reaction, and we recycle this catalyst by simple filtration techniques, and then we reused it again for several cycles, and we found that the catalyst offers excellent yield even after 6 cycles. It indicated the stability and the high catalytic activity of this catalytic system. And when we check the FTIR analysis of fresh and reused catalytic systems, and this is the conclusion. Developed a novel, efficient, heterogeneous monoethanolamine functionalized polyacrylonitrile supporter copper catalyst, and this copper catalyst exhibit high catalytic activity towards 1,4,3 component click reactions in water, and moreover, it is a clean, efficient, and safe protocol for synthesizing 1,4-disubstituted 1,2,3 triazole derivatives, and moreover, this green protocol was found to be general over several substrates with a good yield to excellent yield, within good yield to excellent yield. And this is the first report on monoethanolamine functionalized polyacrylonitrile supporter copper catalyst, and moreover that we can reuse this catalyst up to 6 cycles without much appreciable loss in catalytic activity. And what makes this reaction screen? This is the overall idea of my work, and this work fulfills the criteria of green chemistry principles, that is prevention, atomic economy, less hazardous chemical synthesis, safer solvents, reduced derivatives, catalysis, reuse, and recyclable. Acknowledgement, special thanks to my supervisor and lab mates and Director School of Chemical Sciences, Director MMRC and KVT Environment National Seminar for giving an opportunity to present my work here. And here I am sharing one of my beautiful moments while I am doing this reaction. Thank you.
Arya, you conducted a click reaction.
Yes.
Using the novel catalyst you have prepared.
Yes.
I have few questions regarding your work. One is your system is a heterogeneous system.
Yes.
Then how you have separated the product?
Heterogeneous catalyst.
No, the product, how you have separated the product?
I separated the product through column chromatography.
No, you call out separation.
I mean, from the reaction mixture by simple separation techniques like workup and asking how I separated my catalyst.
Catalyst and product.
Catalyst and product. Catalyst by simple filtration techniques. Like
because filtration means the product is also a solid, I think.
Solid, I dissolve it in ethyl acetate and then filtered the solution.
Filtered the solution for separating the catalyst.
Yeah.
Then evaporated the solvent.
Solvent and get a solid product.
Okay. Because both the products and the catalyst are solid, simple filtration is not enough for separating the product because catalyst is incorporated with the product.
Catalyst is not incorporated. I mean, catalyst is separated.
If you do a simple filtration.
Okay. I dissolve this
Normally
product.
in click reactions, simple filtration is enough because catalyst is a homogeneous system.
Okay, but the main disadvantages of this homogeneous system is the high amount of copper content that is used in homogeneous catalyst, and this may lead to the leaching, and leaching to the product or metal contaminations of product is the main disadvantages for this homogeneous catalytic system. Here we
homogeneous means that is already in the dissolved state.
Dissolved state,
and why we? To the
yeah.
Okay. Therefore, you need additional purification.
Additional purification. I purified this product through column chromatography. That's enough. And I get the catalyst by simple filtrations. There is no other. The product is not incorporated or not stick on this catalytic systems because it is completely dissolved in ethyl acetate solutions.
Okay. You mentioned that it is copper 2.
Yeah.
In the entire process, it remains as copper 2.
Actually, sir, after the reusable teasers, we check the catalyst. We want to check the catalytic state, so we send it to an XPS analysis.
You have carried out an XPS?
It's on processing.
Then what is the need of adding sodium ascorbate?
In CU3, we can synthesize copper 1 by reducing the copper 2 to copper 1. If we directly add the copper 1 to this reaction conditions, but we didn't get a better yield.
But there are reports that copper 2, copper 1 or copper 0 can catalyze this type of click reactions.
I am not sure about the copper 0 state, but I am sure. But
amino group can reduce this copper 2?
Sorry, sir?
Amino group present in your polymer, this support?
No.
No?
No.
It cannot reduce?
Reduce with the presence of copper.
It cannot reduce copper 2 to copper 1?
No.
Sure.
Because we carried out different other reactions, and usually we carried out coupling reactions and CH activation reactions. In that cases, we can't. The NH2 groups didn't reduce this copper.
Have you conducted any leaching studies?
Leaching studies. We carried out ICP-MS studies.
then no contamination of this copper in the solution.
A little amount of leaching is happening there. That's why we get the yield of the product reduces after the sixth cycle. So it is confirmed by a little amount of, we get only 14,277 ppm of.
After the first cycle, you need to conduct the leaching study because majority of the copper will leach during the first cycle.
No, sir. We conduct only after the sixth cycle.
Because other copper catalysts are almost stable after the second or third cycle.
Because it is confirmed by, we get the yield that not much less in the yield of the product after the second cycle.
Okay.
Yeah, I have few concerns, like what sort of evidence you have for the mechanism that you just showed. I didn't see the mechanism fully, but what sort of evidence you have for?
Actually, so we proposed only a possible mechanism for this reactions, and there are all the mechanistic pathway is already understood from the literatures, and it is computationally proved one. The only difference is the attachment of this polymer supporter to this copper catalyst.
So this is a general mechanism?
Yeah, this is a general mechanism for these reactions, and it was confirmed using theoretical studies also.
Yeah, then how fast the reaction is? How fast?
How fast means?
Yeah, rate.
This reaction happens within 7 hours in the case of our catalytic system. The rate, we didn't determine the rate.
So how much millimoles of the reactants you add? You take in all in 1:1:1
1:1.
1:1.
1:1. Benzyl bromide and phenylacetylene we added in 1:1 ratio. Sodium acid is in 1:1.2 equivalent.
Yeah, that's okay. Yeah, so in that 1 millimole you start, right?
Yeah, 1 millimole.
And solvent?
Solvent is the water.
That you have, okay. Yeah, solvent is water. And this backbone, that what sort of effect it is providing for your reaction? So what sort of effect the backbone is providing, or just it is because just
the polymer
you
background
have made it as a heterogeneous purpose only?
This backbone is itself act as a ligand for this copper catalyst.
Yeah, but the polymeric backbone you chose because you wanted to make it as a heterogeneous catalyst so that you can isolate the product and recycle the catalyst. Only because of this you have incorporated.
Because I want to synthesize a heterocyclic compounds, and we choose why we choose this polymeric backbone because we can easily functionalize, or we can tune up this system to. We can tune up the system.
Yeah, that is why I asked. You are saying that you want to tune. Then there should be a rate acceleration or something should happen.
And that may be.
Or else we can take any polymer and that you can filter, and anyway the copper will do its job, right?
Yeah.
So yeah, why you chose exactly that particular polymer? You have some.
It's polyacrylonitrile.
Yeah.
It's solvent resistant. The polyacrylonitrile is a solvent resistant one. And it also a good abortion and resistance capacity is high for this polyacrylonitrile system. Okay. That's why, and easily we can there are so much of possibilities are there, and we can check a better reaction conditions, or we can check a better
this is happening in ambient conditions, right?
This is an ambient condition.
Conditions, yeah. So if you can make some other backbones,
okay,
then maybe you can complete. Can you complete the reaction maybe in minutes or something? In minutes. In few minutes the reaction will be over.
Okay.
Because you have the advantage of the maybe it is not just making heterogeneous, but instead it will give some electronic environment. So steric and electronic environment that will control the copper center, and then you can make it a high rate enhancement can be achieved.
Okay.
So yeah.
Actually, sir, I am doing this in this reactions. I am modify using monoethanolamine, and at the same time I am using an amidoxine. I changed it to an amidoxine group, but I didn't get a better yield. I am only making that amidoxine group. So I didn't go further reactions just because.
Okay. But you will change the backbones and see
Okay.
how. Yeah. Thank you.
Next on stage, we have Devu Chandran. Judges please note code GCH02. I repeat, code GCH02. Next, we have Fatima CS. Judges please note code GCH03. I repeat, code GCH03.
Good morning, everyone. My name is Fatima CS. I am from Maharajas College, Ernakulam, and I'm here to present my research work on the title Intelligent pH Responsive Food Packaging Films Based on Carbon Content Composite, a Green Perspective. Actually, most of the packaging film that we are using today is based on petroleum-based materials, which are causing many environmental concerns because of their non-biodegradability. So, in order to address this problem, we have focused on developing a sustainable and eco-friendly pH-responsive packaging film by incorporating carbon condensates into polyvinyl alcoholic matrix. Actually, we have synthesized this carbon condensate from a renewable feedstock, that is from pineapple leaves, and we have chose PVA because of their biodegradability, so that we can make our composite film more sustainable and eco-friendly. And the resulting food packaging material is to enhance the preservation and safety of perishable foods like seafood products, meat and chicken, especially for prawns. And why we choose this carbon condensates? Let's find out. Actually, the carbon condensates are zero-dimensional spherical nanomaterials with a diameter less than 10 nanometer, and these have very excellent properties like chemical stability, environmental friendliness, then tunable photoluminescence, UV barrier properties, antimicrobial characters, and mechanical stability, biocompatibility, and they can prepare in cost-effective preparation is possible because they can prepare from any natural carbon-containing sources, especially from agricultural waste materials, food waste materials, even from microorganism materials, and all these properties are essential for a food packaging material. That's why we choose carbon condensates. And coming to the materials and methodology, we have synthesized the carbon condensates using a green synthetic strategy, that is hydrothermal one-step synthetic strategy. As I said, I have chosen pineapple leaves as my carbon precursor, and using hydrothermal method, I have synthesized CQDs in solution form which exhibit blue fluorescence under UV light. And in order to prepare the composite films, once again we have chosen an economically and simple method, that is solvent casting method, and we have used anthocyanin extract from jamun seeds, which is again a waste material, along with a CQD solution to prepare composite films. I have prepared 3 varieties of composite films by varying the amount of CQD solution. And we have synthesized the synthesized CQDs are characterized using all these techniques. And we have studied the functional properties of the composite films, which are essential for a good packaging film, such as mechanical strength. We have studied the tensile strength of the composite film, elongation at break property, and Young's modulus. And we have also studied the water resistant properties of the film by studying swelling index, moisture content, and solubility. We have also checked the biodegradability of the material through soil burial method, and we have also studied the UV barrier properties, and we also study the pH sensitivity of the food packaging materials, especially for volatile ammonia, formaldehyde, and triethylamine. And these are the results. coming to the characterization of the CQDs, we have determined the particle size through SEM study, and we have understand that our particle, that is CQD, is under 10 nanometer, exact size is 8.06 nanometer. And this is the FTR spectra, and through this spectra we have identified the various functional group present in the CQD, which include OH, then methylene group, CN bond is there, and COC bond is there, along with the carbonyl groups. And this is the Raman spectrum of CQD, and here we can find out the characteristic D band, that is around 1349, and G band around 1571. Additionally, we got a 2D band which is at 2500, and we also calculated ID by IG ratio, which is approximately at 0.7, which confirms the graphitic core in CQD structure. And this is the optical properties of CQDs, and we got absorption at 270 nanometer for UV visible spectra, which confirms the pi to pi star transition in CQDs. And this is the PL spectrum of CQD, synthesized CQD. This shows the tunable photoluminescence of our CQD materials, and these are the PL spectra in various excitation wavelengths ranging from 300 to 400 nanometer, and we got maximum PL intensity at 360 nanometer. And this is the appearance of CQD solutions in daylight and UV light, and these are the images of PVA composite in daylight as well as in UV light. And these are the functional properties of anthracyanine PVA composite film that we have studied. The first property is mechanical property. As you can see, PVA shows only 13.74 tensile strength, and that increases by adding CQD to the PVA matrix up to 34.78, and there has been an increase in elongation at break as well as Young's modulus while adding or increasing the content of CQD into the PVA. And these are the UV blocking properties of our PVA composite films, and as you can see from the image, PVA alone film shows 37.16% of transmittance for transmittance of UV lights, whereas our composite film shows less than 10 transmittance for UV lights. And these are the biodegradability studies through soil burial method. As you can see, our composite films almost shows same biodegradability as that of PVA, even though there is a slight decrease in while increasing the content of CQD, we can say there is almost same or nearly same biodegradability as that of PVA. And coming to the water resistant properties, as you can see from the table, while we are increasing the CQD content in the PVA, there is an increase in water resistant properties, as you can see from the table. Moisture content, swelling index as well as solubility is decreasing while we are increasing the content of CQDs. And another one is the spoilage detection study. These are the colors developed when the CQD solution, composite solution, is mixed with various chemicals like HCl, formaldehyde, triethylamine and ammonia. Actually, we have used triethylamine and ammonia because these are the gases developed during the spoilage of seafoods, and these are evident from the UV visible spectra. And this is the pH sensitivity. Our composite solution is changing color from pH 2 to pH 40. That is evident from the UV visible spectra. And this is actually the application of our composite film solution, composite films, that we have dictated volatile ammonia as a spoilage indicator in prawns. These are the images before the exposure of ammonia. Actually, we have poisoned this prawns with 1 millimolar of ammonia solution, and we have kept this samples for 10 minutes. So it developed a distinct color change after exposure with ammonia. It indicates that it can be used for the spoilage indication in prawns. And we have also assessed the quality or freshness of the prawns by storage experiment. In first row you can see the images at day 0, and after 2 days of storage the color, a distinct color is developed in the composite films that shows that it can be used for the monitoring, freshness monitoring in prawns. And coming to the conclusions, as I said, I have synthesized the CQD through hydrothermal method in order to avoid the hazardous solvents as well as to reduce the wastage. And we have improved the film properties by addition of CQDs. We have imparted mechanical characters and water resistant properties as well as UV blocking properties to the PVA films, and we have also synthesized a pH responsive film which can be used for the detection of ammonia, triethylamine, which are the spoilage gases released during the spoilage of seafood items, especially in prawns. And we can also detect the formaldehyde that can be added as an illegal adulterant in order to extend the shelf life of seafoods. And we can also detect the volatile ammonia using our composite films, and it can be used for the prawns quality assessment. These are the conclusions and these are the references. And this is acknowledgement slide. Actually, I had thanked for Dr. Shobi Daniel, that is my guide in Maharajas, and I thank my collaborator and our principal as well as HOD. Thank you.
Fatima, whether your compound is toxic?
Actually, the CQD solutions is already reported from pineapple leaves, and it has been used for wound healing properties, even though I am studying the cytotoxicity and the result is in process.
Okay. And regarding the application,
Yes, sir.
you have added ammonia over prawns.
Over prawns, yes, sir.
Why you haven't directly checked the decay of prawns using the
I have already shown that.
shown? Show me.
I have conducted the storage experiment, sir.
In day 1, day 0, the third one is after color change after adding ammonia.
No. This
All
is
these
storage
are-
experiment.
Okay,
Yes.
okay. Fresh.
I have just kept the fresh samples, and after 2 days, I recorded the image. This is the ammonia exposure with ammonia studies. Because we cannot confirm that I cannot say ammonia is only releasing during the spoilage. There may be another chemicals
That
like
may be,
triethylamine,
maybe ammonia,
diethylamine,
maybe
yes.
like that.
That's why I choose ammonia as well as.
Then what is the and your composite preparation? What is the logic of adding anthocyanin?
Actually, sir, I have code color change in higher pH, like pH 11 to 14. In CQD solution itself, I want to study the full pH range. That's why I have incorporated anthocyanin.
Why anthocyanin?
Because anthocyanin can be used to study the lower pH level, that is acidic level as well.
It will undergo color change.
Yes, sir.
Okay. Then what about the temperature of preparing this nanoparticle?
Actually, 180 degrees Celsius hydrothermal. In autoclave, we have set 180 degrees Celsius. Hydrothermal method, sir.
What about the reproducibility of the process? Whether always you are getting the carbon dot particle size between 6 and 10, or majority of the particle size are at 8.
Yeah,
Have you made any reproducibility studies?
No, I have didn't yet. Yes.
No.
Actually, I have prepared CQDs before for food packaging application, not from the source, actually from water hyacinth fiber, not from the source, sir.
Oh.
And we got same CQD under 10 nanometer, not from the source, but I have done this before.
Okay. Yeah.
From my side, can you just quantify the ammonia?
10 millimolar solution is added.
No.
Oh.
During this spoilage.
No, sir, I have done it yet. Actually, we are planning.
So only by seeing the color,
Yes.
you are, but
Yeah.
maybe a
Actually,
quantitative, yeah.
Yeah, only quantitative. When we increases the amount of CQD, that you can see, when we CP5 is actually containing 5 ml of CQD solution. So when we increases the amount of CQD, there is a distinct color change than that of CP1, which contains only 1 ml of CQD solution. Like that, I can differentiate.
And in your material, what sort of change happening when ammonia is detected?
Actually, I think that is due to the, I didn't study it. We anticipate that may be due to the CQD ammonia interaction. Because when we take the diluted CQD solution and when we add ammonia, it's changing the color to brown, light yellow.
Is it just interaction or some sort of chemical
I didn't
reaction?
study it, sir. I didn't study it yet.
And is it reversible?
I didn't study it.
Okay.
Thank you. Yes, sir. Yes, yes.
And even though like the presence of anthracite and PV changes its color with respect to the change in pH.
You are saying not with CQD itself and the cyanide. I have already cleared that. With CQD solution itself, I am getting color change in higher pH. Like about 8, I am getting CQD with CQD solution and PVA itself. I want to complete the pH. That's why from the lower pH side, I want to study. That's why. Yes, sir.
So when there is no need to check the pH at lower level.
I just want to study the lower pH as well. That's why but in case of formaldehyde, I cannot detect alone with CQD solutions. Formaldehyde is not detectable with CQD solutions alone. For that, I have to incorporate anthocyanin. Just want to study the lower pH as well. That's why I incorporated anthocyanin. I have done it along with CQD solutions as well. We are planning to compare this data. Thank you.
Blank test without adding carbon dot, anthocyanin alone, anthocyanin is composite alone, composite without carbon dot.
No, sir. Actually,
Then how you can say that carbon dot is the responsible color change, whether it is anthocyanin is responsible for the color change?
I have done it with CQD alone, without anthocyanin. With PV and CQD alone, I am getting result for higher pH, like about 8. Not for lower pH, for higher pH. Thank you.
Next on stage, we have Meera Gopinath. Judges, please note code GCH04. I repeat, code GCH04.
Good morning, one and all. Myself, Meera Gopinath. I'm a research scholar under the guidance of Professor Dr. Shobhi Daniel. And this is my topic, Green Chemistry Approach to Pyrimidine Synthesis, Molecular Docking, ATMET Analysis, and In Vitro Cytotoxicity Analysis. As the title indicates, we are focusing on green chemistry principles. The constantly changing environment and the toxic chemicals are demanding better yielding protocols from synthetic organic chemists. So, we are planning to invent new reaction methodologies that follow these 12 green chemistry principles. As you know, pyrimidine is a very resourceful small molecule. As per literature, it is a key intermediate in drug synthesis. It acts as a better coloring agent. It is a better chemosensor for transition metals and also a catalytic precursor. So, the importance of pyrimidine always excited the synthetic organic chemistry. So, there are a lot of reaction methodologies are present for the synthesis of pyrimidine. From the literature, these are those methods. So, we planned to do a new reaction which is under ultrasonication in presence of a green solvent and without catalyst. For that, we tried this reaction using 1,8-diaminonaphthalene and para-nitrobenzaldehyde. and we obtained a red solid as the product with a molecular ion peak of 292.1091 in LCMS with a melting point in the range 190 to 191. For confirming the structure of the molecule, we done proton NMR and C13 NMR, and we found that we synthesized 2,4-nitrophenyl 2,3-dihydro-1H pyrimidine. Further, we done the control experiments, and from the control experiments, we confirmed the optimized reaction condition as this, and we synthesized 3 different nitro derivatives from moderate to excellent yield. And the reaction mechanism from literature is as follows. There will be an imine formation at the amino position of 1,8-diamino-naphthalene by the elimination of 1 molecule of water. Further, a nucleophilic attack happens and furnishes the product. As you know, these products have been there, so we needed to analyze the potential of these molecules. You know, lung cancer has been the deadly disease from past decade. There has been 2.48 million new cases and 1.48 deaths has been reported in 2020. So, to analyze the potential of these molecules as anti-cancer agent, first we done the molecular docking. Molecular docking using Schrodinger's suit. And the target proteins were fixed as EGFR and CDK2 while referring to the co-crystallized ligands erlotinib and AZD5438. This is the results we obtained, the glide score and the docking score. From this is clear that one of our compound 3C has shown similar results to the co-crystallized ligand erlotinib in the case of EGFR, but in the case of CDK2 you can see our values were comparably low than the co-crystallized ligand. So for analyzing the interaction on the active site of the protein, we took the 2D interaction diagrams. You see the 2D interaction diagram of the reference compound along with our compounds, and here we can see the 3C molecule which has shown the comparable result has formed hydrogen bonds on the active site of the protein. In the case of CDK2 also we analyzed, and there has been shown AZD5438 has shown multiple hydrogen bonds while our compounds have shown 2 or 3 hydrogen bonds. This is the 3D interaction diagram of respective ligands on the active site of EGFR. This is how the ligands occupy on the active site of respective protein EGFR. In the case of CDK2, our ligands occupy like this. It's almost similar. I'm not saying the exact same, but they show similarity. Further, we done the ADME analysis of pyrimidine molecules using cis-ADME, PROTOX and ADMET-Lab 3.0. From that, first we check the oral bioavailability of these drugs, and this has been shown in this slide. It is past Lipinski rule of 5, Gauss filter, Weber's rule, Egan's rule and Muget's rule. That means this is highly bio-oral availability has been shown. Further, we check the toxicity of these molecules using these 3 tools also. This is a boiled egg plot from cis-ADME. As you can see, our molecules have been, since these are derivatives of nitro group, they has been shown a single position in the yolk region. That means it can bury the blood-brain barrier, that can be permeant, and also it has high gastrointestinal absorption. This is the toxicity analysis from ADMET-Lab 3.0. These 3 charts shows the toxicity parameters of these 3 molecules. Our molecules has been classified as classified as class 4 drugs, and further we done the in vitro MTT analysis of this molecule for lung cancer cell line, and these are the values of IC50 values of respective ligands, and we found that one of our molecule 3C can be act as a potential agent. This is a quantitative data of MTT assay. From this we hope that 3C can be modified as a potential anti-cancer agent. And these are the conclusions. We yielded pyrimidine derivatives using ultrasonication ethanol without catalyst, and our ligands have shown comparable docking scores, and all molecules have been satisfied Lipinski rule of 5. The cytotoxicity assays confirm strong anti-cancer potential. These derivatives show promise as anti-cancer candidates with favorable synthesis. I would like to thank Professor Dr. Shobi Daniel, my supervisor, Professor Dr. Anilkumar Gopinathan, my former guide, Dr. K.R. Rohit, my brother, Dr. Sindhu Matai for Aspire Fellowship, and all the coordinators of this program, along with my lab mates and friends. Thank you so much for your time.
So, firstly,
Yes, sir.
I just wanted to know how you come to synthesize this molecule. How you arrived into these molecules?
So pyrimidines have light structural similarity with pyrimidines. Pyrimidines are potential anti-cancer agents. When we take any molecule, even though erlotinib, there is a pyrimidine ring. So pyrimidine is less explored, even though they are easily synthesizable. Because as you can see, it's a 20 minutes reaction time. Just a mechanochemical process is required. Green solvent, we can do it in room temperature. It can easily separated and easily recrystallized. So I thought if pyrimidines can do, then pyrimidines can also. I'm not arriving in a conclusion.
Yeah.
There's a long way to go, but we are planning to do that.
And do you have some derivatives on the amine side?
No, sir, not yet. On the amine side, we couldn't get a derivative yet, but we are planning that also.
And also, how about the biocompatibility of these molecules?
Sir, as per the in silico toxicity studies, these molecules are less toxic as compared to the database that are available today. But we could check that in the process. We don't know how it acts on a living organism.
Actually, whether you do any cytotoxicity experiments?
Yeah, we done MTTSA only. Yeah, but other results have been, we are planning to do.
No, you perform a docking calculation.
Yeah.
How do you confirm that the crystal structure used is exactly what you follow in your cell lines? That means you reported some cell lines.
Yeah.
So actually people do the experimental comparison in the docking studies.
Yeah.
The exact crystal structure in the cancer cell lines are used for docking studies. Whether you confirm that?
Yeah, we synthesize the molecule and that.
No.
Yeah.
I am not talking about the molecule selection. I am talking about the receptor, protein structure selection. The crystal structure you used for the docking calculation.
Yeah.
Whether it is
sir is
in the cell lines,
yeah.
cancer cell lines.
Yeah, we actually MTTSA has been outsourced, so we told them to do the exact same. So as per them, it's the same.
No, as per the literature, whether you search in the literature that in this particular cell lines, whether this
Yeah.
structure of the protein is available.
Yeah, EGFR and CDQ2 is available.
In that cell line.
Yeah.
Particular cell
Yeah.
lines. Then I think you go for some comparison study of this binding score with your inhibitory concentration assays.
Yeah, it's actually the trend is same. Docking scores trend and the IC50 values have been in a same line, but we have to do further to confirm that.
Whether you used a domestic microwave or microwave synthesizer for this process?
Sir, we used ultrasonication. So
Ultrasonic?
Yeah.
Okay.
Ultrasonicated.
Then what is the need of this ethanol? You can simply prepare the compound by mechanical
Yeah,
mixing.
mechanical strength grinding has been, but our probe is making some problem with the solids. So in a solvent medium, that will be more effective. That's why.
Normally, you can increase the yield or?
Yeah, yield is also increased and reaction time also decreased. Maybe due to the solvent medium.
Okay. Then why you selected this naphthalene derivative, 1,8 naphthalene?
1,8-diamino naphthalene, first of all, it's easily available and it's easy to handle. That's why.
No other option.
Yeah, no other option.
Okay.
What is the yield?
We got up to 90%.
Only one system?
What's
Only one compound is synthesized?
No, 3 derivatives and others are.
You vary the
varied the aldehyde and others are on way.
Okay.
Characterization studies are going on.
Okay.
Okay, thank you, sir.
An announcement. All the delegates can have lunch. It is arranged in the Marian Hall. Please join back at sharp 1:30 p.m. for the plenary lecture 4. Oral presentations will continue here. Participants are requested to kindly stay back. I repeat, oral presentations will continue here.
ഹായ് ഓൾ ആസ് എ സ്റ്റുഡൻറ്റ് നമുക്ക് 4 ലെക്ചേഴ്സ് ഉണ്ടായിരുന്നു. ഇതിനകത്ത് അയ്യോ വേണ്ട അവിടെ കേൾപ്പിക്കണ്ട, ഈ ഷെവിൻ പിന്നെയാണ് നശിപ്പിച്ചത്.
ഹായ്, ഞാൻ ബ്ലെസ്സി. ഞാൻ ഫസ്റ്റ് MSc സ്റ്റുഡൻ്റാണ്, MSc കെമിസ്ട്രി സ്റ്റുഡൻ്റാണ്. എന്നെ സംബന്ധിച്ച് ഈ സെമിനാർ വളരെ ഫ്രൂട്ട്ഫുൾ ആയിരുന്നു. 3 സെക്ഷൻസ് കഴിഞ്ഞു, വളരെ ഇൻട്രാക്റ്റീവ് ആയിട്ടുള്ള സെക്ഷൻസ് ആയിരുന്നു. അതുപോലെ ഓറൽ പ്രസൻറ്റേഷൻസ് വളരെ ഫ്രൂട്ട്ഫുൾ ആയിരുന്നു. സോ ഡെഫിനറ്റ്ലി ഇതൊരു മെമ്മറബിൾ ഡേയ്സ് ആയിരുന്നു. അതുപോലെ ഒരുപാട് പേരായിട്ട് ഇൻട്രാക്ട് ചെയ്യാനും ഒരുപാട് കാര്യങ്ങൾ, ഇൻഫോർമേറ്റീവ് ആയിട്ടുള്ള ഒരുപാട് കാര്യങ്ങൾ കളക്ട് ചെയ്യാനും സാധിച്ചു. താങ്ക് യു തേവര കോളേജ്.
ഹായ്, മൈസെൽഫ് ഷാന. ഞാൻ ഫസ്റ്റ് PG സ്റ്റുഡൻ്റാണ്. എന്നെ സംബന്ധിച്ചിടത്തോളം ഈ സെമിനാർ ഒരു വലിയ എക്സ്പോഷർ തന്നെയായിരുന്നു. ഒരുപാട് ഇൻഫോർമേറ്റീവ് ആയിരുന്നു ഈ സെമിനാർ. അതുമാത്രമല്ല, ഒരുപാട് ഡിഫറെൻറ്റ് ടൈപ്സ് ഓഫ് സ്ഥലത്തു നിന്നുള്ള ഒരുപാട് ഇൻഫോർമേറ്റീവ് ക്ലാസ് അറ്റൻഡ് ചെയ്യാനായിട്ട് പറ്റി. അതുമാത്രമല്ല, കുറച്ചും കൂടി ഈ കോളേജിനെ പറ്റി, അതുപോലെ തന്നെ നമുക്ക് എന്തൊക്കെ പോസിബിലിറ്റീസ് ഉണ്ട് ഈ കോഴ്സ് കൊണ്ടെന്നും, എന്തൊക്കെ ഫീൽഡ് ഇതുവരെ കേൾക്കാത്ത ഡിഫറെൻറ്റ് ഫീൽഡ്സിനെ പറ്റി അറിയാനും പറ്റി. ഓൾസോ ഈ സെഷൻ ഭയങ്കര എൻ്റർടൈനിങ് ആയിരുന്നു. അതോടൊപ്പം തന്നെ ഒരുപാട് കാര്യങ്ങൾ നമുക്ക് മനസ്സിലാക്കാനും പറ്റി. ഓവറോൾ ദിസ് വാസ് എ വെരി വാല്യുബിൾ ആയിട്ടുള്ള ഭയങ്കര എക്സ്പീരിയൻസ് ഒക്കെ കിട്ടാൻ പറ്റി. സോ ഇറ്റ് വാസ് എ വെരി ഫ്രൂട്ട്ഫുൾ സെഷൻ. താങ്ക് യു.
പറഞ്ഞോ.
Schematic representation of the successful execution of the work on collaboration with Dr. Vijay Sri, College for Agriculture, Trivandrum, Vellani. And the pheromones used was 4-methyl 5-nonanol and 4-methyl 5-nonanol in field studies. And these are the initial field trials. We have incorporated the pheromones with a concentration of 500 milligram and 18 milligram in the gel matrix, and the average values shows that the gel incorporated matrix shows a 50% efficiency with respect to control. Now, as a conclusion, three-dimensional hydrogel was successfully developed. The field trials were conducted using pheromone injector matrix against red palm beetle, a major clear trend pest. A lower concentration of 18 mg and 500 mg of pheromones mixture in the matrix was compared against a control, and the pheromone injected gel matrix shows positive outcome with satisfactory drug release. Acknowledgements. I would like to thank my guide, Dr. Dish Krishnan, Dr. Saji Alex sir and Dr. Ajay Kumar sir for the support, my group members and lab mates, my family, Dr. Vijayashree, Assistant Professor, College of Agriculture, Velaini, CCIF and CSINS for the technical support. Thanks to the organizers of KVT 2024 and Kerala Government for Police Fund. Thank you.
Yes, Swati. So this one you have applied, right?
Yes.
So you said that 50% is efficient.
Yes.
So how do you say that?
So from the average value, we have set at the coconut, the fly trap, and then we found that within the duration of 4 months, the T2 and T1 shows the average downfall of 1.86 and 0.625 with respect to control, which shows the number as 1.36. So if we calculated that, the efficiency of the matrix was more than 50%.
Yeah, and how long this molecule?
So actually this study is on the way, and up to 4th month it showed that much of efficiency.
Okay. Yeah, so it takes time.
Yeah.
And
within the end of 4 to 5 months we will get the final.
And then how you synthesized that molecule?
By simply coupling.
Have you shown that? No.
We have shown only the gelator molecule.
So you have made the molecule in the laboratory?
Yes.
Okay. And how many derivatives you have made, maybe?
For this work, we have done 2 derivatives, and one more derivative is undergoing this study.
So if you derivatives appropriately, then you make a better activity.
Yes, sir.
So that is the plan.
Yes.
Okay, fine.
That is the molecule, pheromone molecule? No.
No, sir.
That is a cage.
This is the molecule.
This is the molecule. Then the 10th slide, another molecule is shown. No.
This is the
next one. No. Beetle along with the beetle.
Yes,
No, next one. This one. What is that?
So these are the structures of pheromones. That is 4-methyl-5-nonanol and 4-methyl-5-nonanol.
That is the pheromone.
Yes, sir.
And the previous structure, what is
What?
the bulky molecule?
That are the gelator molecules.
Gelator.
Yeah.
This pheromone molecule, where you collected?
We have synthesized.
This pheromone.
Yes.
No derivatives.
Yeah.
Only this one. That is a non-compound. Okay. And my question is how cost effective this one is?
Cost effective, it took less than 2,000 rupees for the synthesis. Below 2,000 rupees for the synthesis for the work.
Then efficiency, cost effectiveness and efficiency comparing with the existing pheromone in market.
That is more than because by
equally efficient or more efficient than the one available in the market.
It is more efficient than the one available from the market that we have.
Same concentration. Okay.
Thank you.
Moving forward with presentations on the topic wastewater treatment, we have P. Dhanyasree on stage. Judges, please note, code number WWT01. I repeat, code number WWT01.
Good afternoon all. Welcome to my presentation. I am Danyashree, research scholar under the supervision of Dr. P.M. Sabura Begum and Dr. Yusuf Karuvat in the Department of Applied Chemistry, CUSAT. Today I am going to present a part of my research work, the topic entitled Chitosan Nanocomposite Sensor Film for Real-Time Detection and Removal of Mercury from Water Bodies. In our solar system, Earth is the only planet that supports life, that is the presence of water. The access of a clean water is a basic human right by the international organization and governments all over the world. In India, government takes several initiatives to improve the quality of water. Unfortunately, there is no better wastewater management system or strict rule or penalty against the misusage of water. These are some newspaper reports that shows how drastically the water pollution are increased in India. The water pollutant that we can mainly classify as organic pollutant and inorganic pollutant. In my research work, I mainly focused about inorganic pollutant like heavy metals. These are some heavy metals and their Indian standard limits are shown in this table. From the list, we can see that mercury that's only in a nanomolar concentration. Therefore, the detection of a mercury is a highly challenging one. Next, the mercury is released into the aquatic system mainly by two processes. One is the natural process, second one is the human-made activity. The natural process by volcanic eruption, coal combustion, etc. The human-made activities like industrial aspiration and use of pesticides in the agricultural field, etc. There are so many sophisticated techniques are available for the detection of mercury like stripping voltammetry, cold vapor atomic absorption spectroscopy, etc. But in my method, I switch on to a better alternative, that is colorimetric method. It is low cost and get efficient result, and the main advantage is that we can visually detect whether the water is contaminated or not. And the researchers are constantly searching for a sustainable material for the simultaneous detection and removal of mercury from water sources. So I combine the green polymers of chitosan starch in a optimum concentration, I get a composite film, and the incorporation of nanoparticle get a brownish yellow colored sensor film. With the presence of mercury, the color of the film changes from brownish yellow to transparent. The basic mechanism behind this process is that the nanoparticles, that is silver, that undergo redox reaction in presence of mercury 2 plus ion, the silver that converted into Ag plus and Hg2 plus that converted into Hg0. Why I choose chitosan and starch? The chitosan and starch have so many functional groups like OH and NH2 group that has another property that easily adsorbs mercury from the water. So therefore, they enhance the adsorption property of the mercury. Next, the silver particle I prepared in a greener method using a novel source of pothos candace leaf extract, and is widely seen in Kerala. It is a medicinal plant. From the UV absorption spectra, we can see that there is a peak at 430 nanometer that confirms the presence of silver nanoparticle. And the TEM image shows that the particle size is about 8 nanometer. And moving to the analysis of chitosan starch silver nanocomposite film, that is our sensor film, the peak at 430 that represent the silver nanoparticle present in the composite film, and the FTR spectra. From the result, we can see that there is no interparticle interaction between the silver nanoparticle and the composite film. And the XRD analysis, we can see that there is a peak at 38 degree remains in the sensor film, that is the presence of silver nanoparticles in a lower concentration, that is 0.1 weight percentage. Moving to the quantitative analysis, from the result, we can see that by the addition of 0 ppb to 60 ppb of mercury ion solution into the water, there is a linear decrease in the intensity of the absorption peak of the nanoparticle in the composite film, and this is the correlation diagram. The first one is the photograph of the composite film. After it's dipped into the 100 ppb solution of mercury 2 plus, the color of the film changes from brownish yellow to bright yellow, and it is dipped into the 100 ppm solution. The color of the film changes from brownish yellow to transparent. This is the UV absorption spectra By the presence of mercury, the absorption peak at 413 that began disappeared because the formation of AgHg amalgam formation undergo redox reaction. And the selectivity of the composite or the sensor film is very important. So I analyzed with various metal ion solution. From the result, we can see that the sensor film has a higher selectivity towards mercury only. Next, the interference studies are also carried out using metal ion solution and some organic dyes. From the result, see that there is only a lesser or negligible difference in the absorption intensity, and by the presence of mercury, the peak becomes disappeared. And also, real sample analysis also done with water resources like drinking water, tap water, and river water from the locality. And the results show that there is no mercury in the neighboring water resources. By the addition of mercury 2+ ion, the peak becomes disappeared. By comparing the previous literature reports, we can see that the present work has an efficient LOD than the previous one, that is 0.4 ppb. And it also another property that mercury removal, that is 99.29% of a mercury can be removed by a single piece of sensor film. Moving to the conclusion part, it is highly efficient for sensing removal of mercury 2+1 water samples and is economical and environmentally benign in nature, stable ambient condition both basic and acidic, that is pH 2 to 14, and highly selectivity towards Hg2+ ion and visual color change on interaction with mercury, and LOD and LOQ values are 0.4 ppb and 1.2 ppb respectively. And the real-time real sample analysis also studied, and the capability of Hg2+ ion removal can be analyzed by using Hg analyzer, and the result shows that 99.29% of mercury can be removed. These are my reference papers. Thank you.
Tanya, what is the role of this chitosan in this study?
It acts as a film. It has itself have a property
is
like
powder,
polymer. Yeah.
Polymer powder form.
Yes.
And how you transform into film?
It can be dissolved in acetic acid solution. 2% of acetic acid solution we can dissolve to a particular film formation.
Okay. For making film only, you are using this,
Yes.
no other role.
It has adsorption property.
Okay.
The chitosan has a NH2 group and OH groups are freely available in the
Therefore, it can
skeleton.
absorb this silver ions. With
No,
the-
mercury ions. They are adsorbed mercury ions.
In
from
presence
the
of silver only, the mercury can be visualized.
Yes, sir.
Initially, you absorbed silver. Paste film of silver. No. You have used chitosan directly.
No, sir.
The film of chitosan directly for detecting mercury.
No.
Have pre-processed using silver.
Yes, sir.
Then initial absorption by silver.
Yes.
How much percentage of silver?
0.1 weight percentage.
0.1. Then the color changes to yellow.
Yes. Brownish yellow.
Brownish yellow. Okay. And in that on that film, you can absorb mercury.
Yes.
Okay. Then how it can purify the water? Simply dipping these things in water cannot purify, more like that.
By putting this 1 or 2 piece of the sensor film, the mercury will form a amalgam formation on the surface of the composite film, and we can
That
easily
is in the
remove
case of a small glass of water. If mercury is there, you dip a piece of this film, it will absorb.
Yes, sir.
But in large quantities of water, river water, how these things work?
We can modify into several types like a hydrogel or some type hydrogel beads. By making this composite solution, we can transform to another form like hydrogels and hydrogel beads.
Okay. How you analyze the SEM? Using SEM, how you analyze the surface more?
The particles are equally distributed. That is, nanoparticles have no agglomeration is there. They are uniformly distributed on the composite.
Whether the silver is replaced by mercury or like that? No.
There is an amalgam formation.
Amalgam. Final composition is composite contains silver as well as mercury.
Yes, sir.
Which method you adopted for?
TEM image for analysis.
TEM image. For ICP analysis? No.
No, sir.
TEM image means localized screening only. Okay. Okay.
And these sort of works are reported, right?
No, sir.
Not reported.
Not reported. Is said no way. Their composition and the nanoparticles are prepared from a novel source of scanned leaf extract. So we can modify the particle size to 8 nanometer by using that extract.
From where?
That is a medicinal plant. Using the leaf extract of that plant extract, we can more tunable their size.
Okay.
The silver is nano.
Yes.
You prepare silver nano by green method.
Yes, sir.
Then that will not leach to the water.
No. We are analyzed the AS analysis, get that the nanoparticles are intercalated into the composite structure.
Not in water.
Note.
Generally, I am asking why this silver nanoparticles are, very usual.
No. The electron potential value between the silver nanoparticle and the mercury nanoparticle, there are the difference between them are 60 microvolt. If it converted into nanoscale, the silver can reduce mercury.
Silver can reduce mercury. And silver get oxidized.
Yes.
Okay, then see, there is a limit for amalgam. You mean amalgam, not
Amalgam formation.
Okay. So there is a limit for detection.
0.4 ppb. Limit of detection, are you asking?
Yeah. What is that?
Limit of detection. LOD value.
Yeah. I'm not asking that. I'm asking that if you exhausted, yeah. Saturated. So
okay.
yeah. So what is the level?
That I have to check.
What is the amount of silver involved there? That much mercury can.
That much mercury. Is it? It is 1:1 ratio.
The reaction is 1:1 amalgam formation.
And for that is, so I am coming to that, very large areas. So that means silver is very costly. So 1:1 silver, how can you use for this one, for absorbing mercury? Because if you, yeah, so it's really maybe.
What about the surface area? The silver has to be on the surface.
Yes, sir.
Then only the interactions happen.
In the removal part, we can also say that the chitosan has another role. Chitosan has an adsorption property.
So you are saying.
Without silver, no detection, no removal.
Is there any removal without silver?
Chitosan have some property, that is the freely available NH2 and OH group have adsorbed on the surface.
There is no selectivity
in
it's the absorption. So you can absorb or other things.
Yeah. So as per your hypothesis, it is coming like.
Activity part and the part will be gone there. It is fully covered with the mercury, then it will not be no longer used, right?
Yeah.
No, we can put another.
Reusability, I'm just asking.
It cannot be reusable. This low cost we can prepare by.
Yeah, maybe for a glass of water or bucket of water it is fine. But if you go in a real application.
If you're using 10 ml or 20 ml of solution, 1 × 1 centimeter
Yeah,
square
an experimental
of
setup is fine, but for practical application.
Sort of purifier, maybe you have to change it once in a 6 months or 1 month.
And this is not reversible.
No.
You can't do anything.
No,
Yeah,
sir.
once the alloy form, amalgam forms,
Amalgam
then
forms.
you can't do anything. Yeah. Yeah, just.
Thank you.
With this, we have come to an end to our oral presentation. Let's applaud all the participants for their efforts and hard work. A big thank you to our judges for their valuable insights and time. Thank you all.
Participants can have lunch. We will begin the plenary lecture 3 by Professor Kana M. Sureshan at 1:30 p.m. Thank you.
നീ അവരെ നോക്കിക്കോളാം. എനിക്ക് ഇഷ്ടപ്പെട്ടു. ഞാൻ സംസാരിച്ചു.
ഞാൻ പുള്ളി വെള്ളം കുടിക്കാൻ പോയപ്പോൾ പുള്ളിയുടെ മുന്നിൽ ഞാൻ ഡാൻസ് കളിക്കുന്നു. പ്രൊജക്ട് ഓക്കെ ഓക്കെ അക്ഷയ് അക്ഷയ് ഓക്കെ ഓക്കെ സോ ദിസ് ഇസ് വാട്ട് ഇസ് ഹാപ്പനിങ് ഇൻ മൈ ലാബ്. ഞാൻ കാര്യങ്ങളൊക്കെ കുറേ സംസാരിച്ചു. ജനുവരി ഞാൻ എക്സാംസ് ഏപ്രിൽ ഓക്കെ this year one too many people in it this year one next one ഞാൻ മര്യാദയ്ക്ക് ചെയ്ത് നിങ്ങൾ നോക്കി പോയി ഫുഡ് കഴിച്ചു. നീ കഴിച്ചോ? നീ എന്താ കഴിച്ചില്ലയോ? ഐസ്ക്രീം വെള്ളമാണ്
Now we use crystal engineering. As he has already mentioned what crystal engineering is, I will give more detail about this. Here example, for example, so this case, this is just a cinnamic acid. This is a perfluorinated aromatic cinnamic acid. Now this arene perfluoroarene is, they form a complex, a charge transfer complex, because this is, can you switch it off please? No, but I don't want to hear that, right? So this one is electron deficient and this is electron rich. If you have a co-crystal of them, they always stack to each other, perfluoroarene and arene, and at 3.4 angstrom unit. That is fixed actually, 3.4 to 3.5 angstrom, because there is an attractive interaction between an electron rich pi system and an electron deficient pi system. So what they have introduced is an electron deficient pi system here, an electron rich pi system here, so that they will form stack, and the distance is 3.5 and they can do reaction along this direction. This is one of the crystal engineering methods. In other cases, this is a still beam with a normal still beam, and this is a perfluorinated still beam. Of course, as I mentioned, one is electron rich, one is electron deficient. They will be at proximity. They can do a reaction along this direction. You see the yield is more than 98%. Usually it's 100% is the yield. And of course, you can also have this kind of system. One of them is electron rich, and one of them is electron deficient. Again, they will form a dimer like this, so that the electron rich and electron deficient will be at proximity. Then you can do reaction along this direction. There are other methods. If you take a pyridine kind of system and a normal benzene discade, you can of course make it electron deficient by adding a H+, right? Just by adding acid, you can make a protonated version of this one, and again that will form a charge transfer complex between the pyridinium and benzene. Then you can do reaction. And this is one of some examples of crystal engineering, how to bring them at proximity and do reaction. This 2+2 cycloaddition reaction. And they have increased the complexity. This is all from the literature. I am introducing what the top of chemistry is, right? So here you have two such systems, right? So two double bonds in each molecule. So the pyridine and also pyridine here, and middle is benzene. Now how to bring them at proximity? Here they have used this kind of a phenol, resorcinol kind of thing. And this distance is fixed in the benzene ring, right? This oxygen, 2 oxygen is fixed actually. Now, this will form a hydrogen bond with this nitrogen, and this side also, it will template how to behave actually. So these molecules will be exactly like this, actually forming a hydrogen bond. And in other words, I am fixing the distance between this and this as this and this. So the template fixes the distance through hydrogen bonding, non-covalent reaction. This is another method. You can use charge transfer, you can use this kind of template to bring them at proximity, and you can do this reaction. 2+2 cycloaddition. Now finally you can remove the template. By dissolving in some solvent, you can remove the template and you can get this kind of cycloadduct. And another reaction is a polymerization reaction. If you have diacetylene like this, R can be any group, and if they are arranged like this angle is about 45 degree, and if this distance is about less than 3.8 angstrom unit, and this distance, the R and R distance is about less than 5 angstrom unit. This is geometric criteria for this reaction. Then polymerization will happen like this, and you'll get polydiacetyl. It's a conjugated E9 system, right? It's a fully conjugated, and it's a conducting polymer or semi-conducting polymer you can get. It's called polydiacetylene. But the challenge again is to bring these monomers at this particular orientation in the crystal. In solution is impossible, right? Because they are randomly moving. But in crystal also not very easy. Very specific distance, very specific angle is required for this reaction. I mean, not very specific. Maybe 10 degree here and there is fine. And also 1 or 2 angstrom here and there is fine. But still, we require this kind of arrangement for the reaction to happen. Now, how people have done this? Again, crystal engineering. So this kind of oxalyl amide, this can have a hydrogen bonded system. Like this, it can form hydrogen bond in the crystal. And people have used this oxalamide to bring this kind of diene. This is the monomer, this pyridine containing diene, diacetyl. The R is pyridine here. And this is the oxalamide which will form this kind of arrangement. And you have also a carboxylic acid, 2-carboxylic acid. And this is a base, it will protonate, acid and base will react, right, form a salt. So it will, in other words, this acid will attract to the pyridine ring. So, and already this molecule will behave like this, right, through hydrogen bonding. And this R is an acid. R contains acid at the termini. Now, each R will bring this pyridine unit, one monomer unit here. So, in other words, this template will bring the monomers at proximity, and in a specific arrangement, then they can do reaction along this direction, and you can get polymers. Polydiazine by shining light. Yeah, this is what. So it makes the protonated form as a linear chain, as a linear polymer, and also because of the hydrogen bond. This is the crystal structure. You can see the oxalamide, and this is the pyridine, and it's forming the hydrogen bonded interaction with the pyridine in this case. And that undergoes a reaction, and you get this kind of polydiacetyl having this pyridine unit. Of course, you can remove the template by washing with a base, for example. You can remove the template and you can get the polymer out with a specific pyridyl unit. And you can also change the other way around. You can have this pyridyl unit and you can have this kind of acid. So here, our template is having pyridine unit. The oxalamide is having pyridine unit, and the diene monomer is having acid groups. So that can also be polymerized in the same fashion. So it will form salt like this, and you can do the reaction. This is the crystal structure, X-ray crystal structure, and this is the polymer actually having carboxylic acid. So first they have made base containing PDA, and now this is acid containing PDA. That's all possible, all kinds of possible. Now how about this one, neutral PDA, having a CH2OH, which has further possibility of functionalization, because you can always substitute OH with something else, right? You can functionalize that. So how do they make that? That's also very easy. I believe this is coming. Yeah, it's coming. Yeah, this one, again the same template, having acid. You can have pyridine, but in this case it's not directly connected with the CC, with the system, but through an ester bond. Ester bonds are very advantageous because ester bond is very labile. I mean, you can hydrolyze the ester bond to acid and alcohol. So you have an alcohol group which is connected to pyridine through an ester bond. Now that will dictate this kind of arrangement, pyridine acid interaction. Then upon polymerization, you get this pyridyl ester. That pyridyl ester, of course, you can hydrolyze, you can get this kind of neutral form of PDA. So all these things are possible using PDA chemistry. So in this PDA chemistry, they have mainly used templates, whether base template or acid template or something like that. Please. Yeah, so that's what I'm saying. So finally they get this. So they want neutral. So they wanted this actually, neutral. In the other case, previous case, they want only pyridine. So in that case, they have CC bond. So they have introduced this ester intentionally to remove the, yeah.
How can we bring this proximity in a reaction mixer?
No, not in the reaction mixture, in the solid state, right? Crystals. So this is crystal, this is co-crystal of these two. It's all in the solid state. So that is my problem, right? Whenever I talk about this one, after some time people will think this is a reaction, this is a reaction. Not your mistake, everyone's mistake. How it is happening. So all we are talking about only in solid, right? In crystal. Whatever structure you see is in the crystal. Yeah, this is another reaction. This is, of course, this middle ring of this anthracene is very reactive because that behaves as a diene. And this is a dienophile, electron deficient, this kind of system. And you can make a co-crystal out of this, a charge transfer complex, and you can do a Diels-Salt reaction between this diene and this dienophile. And this is also reported by years ago by J. Kochi. Yeah, this is the crystal packing. Actually, this is the anthracene. This is the dienophile, diene, dienophile, diene, dienophile, one after the other, packed in the crystal structure. and it'll undergo, upon mild heating, and undergo reaction and get the deal salted product. So this is the product. And people have, of course, you can do, once you have a system, this kind of system, chart transfer system or donor acceptor system, you can, of course, change the substituents, right? If you have a bromine, you get this kind of bromo substitute. Of course, you have possibilities of further functionalization using bromine, for example. So all those things are possible. This few others have taken this kind of work. After Jay Kochi published the first paper, then few other, there are 4 or 5 papers on this, a very simple system. This is a sugar. This is not really sugar, isomer of sugar. This is called inositol, having 2-acetone protection. And you can see the difference between these two is they are regioisomers of the same material. Diketal of inositol, this is also diketal of inositol, I have numbered it. This is 1,2,3,4 diketal, this is 1,2,5,6 diketal, they are not same, they are different materials. And this is I have observed, this is by accident we have observed when I was doing a postdoc. This particular material, when we heated, while checking the melting point, we found that it is melting 2 times. I mean, soon after melting, it is again solidifying and again having a second melting. Then we looked at the structure, and we found that this is the whole group is transferred. Now, not an intramolecular transfer, that is not possible, it's very far. So how? So let's see the crystal structure. So this is the crystal structure, this is the ketal which is very in transfer, and this is the OH of the next molecule actually. So this OH of the next molecule. So basically it is stealing a ketal from the next neighbor actually. This is, as you can see, this is the leaving group, this is the nucleophilic, and it's just like an SN2 type reaction. It's happening in the crystal lattice. So almost like a trigonal bipyramidal arrangement. And this nucleophile attacks and it reacts and it takes this ketal. So they form this kind of arrangement and this kind of a polymeric ketal structure. Of course, we did not isolate this, only a proposed mechanism because these will be really labile, I mean, not very stable material. Finally, what we get is this one. This we have structure for. I think this communication is quite slow. So finally, this is what happens. You get all one product. Simple ketal transfer reaction. So far I have introduced what topochemistry is. I have taken 2+2 and what is diacetyl chemistry to make polymers, and also a Diels-Alder reaction which is happening in the crystal, and also much more complex this ketal transfer reaction. Now we are interested in this reaction. This is azide and alkane. They undergo cycloaddition reaction if you heat them. And you don't have any selectivity. This can be like this or like this, depending on the orientation. You get 1,5 substituted or 1,4 substituted isomer. If you take a mixture, I mean, if you take these two in solution and heat, you get both of this, almost 1:1 equivalent. I mean, ratio 1:1 ratio. No selectivity for this reaction at all. This is called Huisgen reaction, discovered by Huisgen. And of course, this is what I have just mentioned. Depending on this orientation, you get this product or that product. But this revolution came when Sharpless and Meldal identified that when you have copper 1 in the system, this was also an accidental discovery. They get only one of these, right? Only this one, selectively, and at very low temperature. You don't need to heat actually at very high temperature. At room temperature, this reaction. This is called click chemistry, you know. Only this is click chemistry. This is not click. This is click. When you have copper, this immediately reacts at very low temperature. So this is click chemistry. We are interested in this this cycloaddition in general using topochemistry. This is in solution so far. So how? Okay, we are interested in crystalline polymers. Polymers usually are amorphous material. Once you make polymer in solution, once you remove the solvent, what you get is an amorphous material. There is no order, long range order, because polymers are really large molecule, right? It's very difficult to crystallize them in a single crystal. You will have some crystalline domains in the polymer, not fully single crystalline crystals. I mean, polymers is very difficult to get. because of the entropy, they will not form a proper crystal. And also there is polymers means there will not be a specific number of monomers, right, in all the polymers. Polydispersity is what it means, right? So it can be 1000 mer, it can be 900 mer, it can be 1100 mer, all those things will be there. So it is difficult to crystallize such a complex mixture. So we are interested in crystalline polymers using our chemistry, that is, you make a crystal of the monomer and polymer is in the crystal, then what you are getting is a crystal of the polymer. That is one of the possibility using Thevara chemistry, right? Because you're doing in the reaction the crystal, then there is a possibility to get crystal of the polymer. So that's what we are interested in, and we are interested in this specific reaction. Of course, challenge is to bring them at close proximity. That I'll tell you how to do that. So this is how we do this. We take some templates, like in the previous case I have shown. So we don't use whatever template they have used so far. So we are taking peptide, for example, which is hydrogen bonded. And you have a head and tail in the peptide, N terminus and C terminus, for example. And always in the crystal, this is known in the literature, this kind of small peptides make stacks of, hydrogen bonded stacks. And between the adjacent stacks, this is one stack, this is another stack, the head and tail will be at proximity. Here also, whether it is parallel sheet, all head will be on the same side, but still between the stacks, head and tail are at proximity. So that's known. So now we want to use that. We will make our head and tail as azide and alkane. So I can bring the azide and alkane at proximity. If so, I can do reaction along these directions. The head and tail are azide and alkane. I can do reaction along this direction. I can get a protein-like molecule, long protein-like molecule. So this is the first system we have taken. Here it's a sugar platform. We have an azide and an alkyne, and this is a fresh crystal. This is after 40 days crystal actually, right? You don't see not much difference between the fresh crystal and the old crystal. But what we understood was when we took the TLC, because this is not reacting, we wanted to do something else actually with this chemistry in solution. And old samples never reacted in solution. Actually, it was not dissolving in solvents. So old sample has undergone something. So when we have taken the TLC, this is what it is, right? This old sample is, it is a mixture of so many things actually, so many spots. Then I told my student, you are lucky. When I see a lot of spots, usually people don't like it. Organic chemists don't like this kind of closed spots, right? Because it's very difficult to purify all those things. Then I told my first student, Achudara, again we have got into this one quite accidentally. So I told you are lucky. I told him immediately run a Maldi. This is the Maldi. You can see the repeating, right? This is, I don't know what mer it is. This is X mer, X plus 1, X plus 2, X plus 3. So all oligomers are being formed in the solid state. So it is oligomerizing or polymerizing in the solid state with time. And also you can see monitored by IR. This is the fresh IR. Soon after crystallization, after just 30 minutes after crystallization, you can see the stretching frequency of the azide, right? And after 48 hours, this is getting reduced. After 10 days, it's almost gone, right? So it is being consumed in the crystal lattice. It's all solid state IR, okay? And you can also do the melting point, right? Fresh melting point is 85.42 or something. Using DSC you can measure. After 1 day, it is reducing, 81, then 74. Third day. What is happening is, you are making oligomers in the parent crystal, or you are making impurity in the system. So what you are seeing is the colligative property, the depression in melting point. In a time dependent manner. As the time goes, you are making more and more impurity, which is the product actually. And that is showing the depression in melting point in this case. So all these things we have done. We do all this for all the reaction. We do this kind of characterization. You can see the NMR. This is a very good NMR of the monomer. Next day, if you take, it's getting complex. No organic chemist will like this kind of NMR again, right? Because it's mixture of dimer, monomer, trimer, everything. So you can see slowly it is getting cleared. At the end of the day, it's, you see, end of 10 days, it's all going to one state because all are going to a polymer. So it's cleared. It's complex here, now it's much more clear. And you can do carbon-13 NMR also. Yeah, this is the powder XRD. You can see fresh monomer. Slowly this says that it is keeping the crystallinity. The sharp peak says that crystalline. It is always crystalline. It's reacting, maintaining the crystallinity. And you can see some peaks are disappearing, some peaks are newly coming because it's going to another phase. Monomer is converting to polymer in a single crystal fashion. Of course, this is finally you can do the crystal structure. You don't need all those things. I mean, all the experiments I have shown, we didn't have the final structure until, we did everything. So finally, we have taken a fresh crystal. This is a crystal structure. As you can see, the azide and alkane are at proximity in a ready-to-react orientation, almost like a transition state for their cycloaddition reaction. And you can see also, this is the packing. They are packed in a head-to-tail fashion, one after the other. And that is why we are getting polymer, right? Otherwise, if two molecules like this, it will make a dimer, cyclic dimer. That's not happening. So the packing is like that. Packing is like that in such a way that it can undergo reaction to form long polymers. Now, if you do crystal structure after a few days of keeping the crystal just at RT, even in the fridge, even at 0 degrees centigrade, you see that everything is reacted. So the triazole has formed. So it's a polymer structure. So it's only time. You make the monomer crystal, keep the monomer crystal and forget for some days and redo the structure. What you have is a polymer. So you don't need to do any reaction. No solvent, no catalyst, nothing. So it's a simple reaction. You make monomer and forget. You're having polymer in this case. Not all the case, all the time, right? But most of the time this is the case. Now we have designed several systems because through crystal engineering again. So all these structures you see are reported actually. They have the crystal structure reported. All of them have very peculiar platform that is the cyclohexyl ring or substituted cyclohexyl. But two OHs, right, which is marked in red. This di-equatorial diol. So they have this kind of arrangement, very common arrangement in all these crystals. That's very conserved. In all the crystal structure, there are many molecules like this. All of them crystallize like this with two hydrogen bonds in a zigzag fashion. So this is what we want to exploit for making sugar polymers. So this is our idea. Have this feature, this diol feature. Take azide and alkane. This is what we expect. This is all a schematic. And you can call it a supramolecular fibril. And if you look along the fibril, the fibril is going behind the board, you would see like this. And of course, in a crystal, it has to pack in 3 dimensions. So this will be packed like this because the azide and alkane can have some attractive interaction. They can talk to each other. They can have pi-pi interaction and also dipole and pi interaction. So then this is the most favorable interaction. This is what we expect. Then we are, in other words, we are placing the azide and alkane at proximity in the crystal lattice. Now we can do this reaction by heating. This will undergo this reaction and we can get glycopolymer, sugar polymer. So see, let's see whether we can get, this is all solution. Okay, here you can see, until this is the solution, right? This is normal solution chemistry. We start with acidogalactose, then protection, deprotection, all those things. Finally, you get this monomer. This is our monomer. So now hereafter crystal chemistry again. So this is a crystal picture. Yeah, sorry. So this is the packing. That zigzag packing we expected is already there. So I have just put one in a 90 degree like this, vertical. So this is the zigzag packing. You can see the azide and alkane are at proximity. The blue line is azide and this one is alkane. They are at proximity. And they react. They react. So this is what? So this is one chain of monomers at proximity. The azide and alkane are in a ready to react distance and they will form 1,4 isomer. This also we know from the monomer structure because they are anti-parallelly stacked. And upon heating about 60 degrees centigrade for a few hours, you can see this is a IR, monomer to polymer. The azide vanished and also the NMR. This is the polymer NMR, proton. This is monomer, again carbon-13. You don't get normally very good NMR for polymers, right? Because you have all kinds of polymers, but here you have polydispersity as 1. So that's why you get very good NMR also in this case. Yeah, so this is what? So this is the polymer structure after heating at 90 degrees centigrade for 24 hours, you get fully polymerized structure. So the monomer is polymerized. Sometimes it's only room temperature, sometimes it is heating is required. So this is what? You make a monomer, crystallize them, and heat it, you are going to get crystal of the polymer. So I have shown you so far two sugar molecules doing this one. We have done with the other systems also. This is the same inositol. Again, this is solution-based chemistry to make this kind of monomer. So simple chemistry, again, we have made this monomer. Here you have that feature 2 times, right? This diol functionality 2 times, this side and that side. And because of that, this is what we expect, a honeycomb-like packing because of the zigzag packing and this the molecule in between. And this is the distance, again, good distance to react. These are all crystal structures. And they react, of course, they react from this kind of polymers. And also, an interesting feature is, we have done a lot of sugars actually, so this is the collection of all the sugars. An interesting feature of this reaction is, normal click reaction, you need a CH or a terminal alkane. Click chemistry, you need a CH, right? The acetylenic CH is required. Here, we have an internal alkane, there is no CH here. So that also reacts because this is a proximity driven reaction. There is no H required. So even this one, this is also similar actually without any CH. Even this is more complex. This is where our monomer itself is a disaccharide. So we have taken that disaccharide and we have polymerase. This is an open chain alcohol and that also we have reacted. So a lot of sugars we have done like this for a purpose. Then move to nucleosides. So the cytosine derivative, all structures are already known in the literature. All of them have very peculiar packing again. So how they pack is like this. So they form an NHN hydrogen bonded dimer as cytosine dimer in the crystal lattice. And they pack along as a tape, or as a molecular tape. I don't know whether I have shown, no. So they will undergo, I have to go back and tell you. Yeah, first they'll form this kind of dimer. Then this dimer will, this is NH, this is oxygen, right? So this will form a tape actually, one after the other. So it will form a molecular tape through hydrogen bond. So that's what we want to use for designing our next reaction. So we take a cytosine having a ribose platform, this is a sugar ribose. You can have azide and alkane as 5' and 3'. And because of the cytosine dimer, this is what is expected, and azide alkane interaction, this is what is expected. Then we can do reaction along this direction. This is our monomer, which we have to make, of course. And we have made that synthesis I'm not describing, it's a little bit complex. And yeah, so this is the structure, crystal structure. You can see NHN dimer, one dimer, so one dimer here, next and next, right? So the distance between them is less than 4 angstrom, azide and alkane. So they react, in this case not in a single crystal fashion, but they react keeping the crystallinity maintained. So this is the monomer NMR, this is the polymer NMR. So what we have made is a DNA mimic, a monobasic DNA mimic, wherein you don't have a phosphodiester linkage, but a neutral triazole DNA. These are called triazole DNA. People have made such DNAs in solution. Up to 9-mer, 10-mer people have made, a Japanese group, very tedious synthesis because once you have nucleobase and also this kind of triazole, it's very difficult to purify from the column. So this chemistry, of course, you can get very easily this kind of oligomers. But there are challenges, we get a mixture of everything. So, yeah. No, that's not possible. So we cannot control the length. In solution says you can stop at 9-mer. Here you have 9-mer, 10-mer, everything. So unless you generate some method to separate them, this is difficult. So this is a similar one. You have an extra, similar monomer, you have an extra benzoate here, N-benzoyl cytosine. Because of that, you have an additional pi-pi stacking as you can see in this dotted line. And that will bring them much more closer here. Actually, previously it was close to 5 angstrom unit. Between them, now it is less than 3.5. Between the azide and alkane, they are in a ready to react orientation. Now, they react at 60 degrees centigrade in a single crystal fashion. This is the polymer, homobasic polymer of the cytosine. It's a DNA kind of analog. It's protected, of course. Yeah, then we went to peptides. A lot of peptides we have done. So I briefly, some interesting features. For example, this is the middle one, this one. We found that when they react, it will undergo twisting. Always goes to right-handed helical twisting. Then we thought that the helicity is decided, the macroscopic response is decided by the molecular chirality. To prove that, we have taken the L form of that, and in that case it always twists in the opposite direction, this crystal twist. And that is the first paper, this PNAS paper was the first paper showing that molecular chirality dictates the motion of this crystal actually, right? This macroscopic response. This is a collagen mimic, this Pax-like collagen, and you can see this can take 1.55 million times. That means 15.5 lakhs times its own weight. This is a 10 milligram crystal. This is only schematic. We have hanged about 15.5 kilogram until it broke. Finally, it broke. I mean, it bends and breaks. So this, the Q came from collagen structure. So collagen is called biological steel, our protein which gives the strength to us. And also, for example, an ant can take 5,000 times its own weight because of the collagen present in its tissues, actually, the legs. Sorry. So this is again isoleucine based peptide and hydrophobic actually. So you can make this polymer and coat on a surface and you can get this kind of hydrophobic surface. This is not super hydrophobic, about 140 degree is the hydrophobic, I mean the water contact angle. So it's a hydrophobic surface you can make. And there are other topologies which were unknown topologies like this cross-stacked and this twist-stacked packing, etc. We have shown with the protein mimics. This is a new reaction we have invented. This is TEAC reaction, topochemical enazide cycloaddition reaction. This is similar to Huisgen reaction. This also comes under Huisgen. Huisgen reaction is a list of reactions. So this is also dipole and this is alkene instead of alkyne. In this case, what you get is triazole instead of a triazole. So triazole is aromatic. This is not aromatic. That means this is not very stable. So this will undergo easily a denitrogenation reaction and upon heating or even shining light, and you will get aziridine molecule, aziridine ring. Now that's very interesting. Now I am talking about making this kind of linkage in the polymer backbone. Now after making the polymer backbone with this kind of linkage, if I shine light or heat, I'm going to change the backbone, right? I'm going to change the backbone to aziridine. Now once you have aziridine in the system, aziridine is very good stuff for an organic chemist or a polymer chemist because you can open the aziridine with any nucleophile. So in other words, you can change the polymer chain with any functional group you want. For example, you can put a sugar. You can open the aziridine with a sugar molecule or a fatty acid, for example, or a fatty amine. All those things are possible. So that's why we were interested in this one. So yeah, we started with this simple diphenylalkyl system, azide and alkane, and that undergo a CSE reaction. This is a regio-specific, not only regio-specific, it gives 1,4, and also stereo-specific, only that particular chirality in this case. And upon denitrogenation, it gives this kind of acidity. And also we have shown, this kind of system, this is having one phenylalanine. This is half helical. Upon reaction, it gives a helical polymer. That also undergoes denitrogenation to give acidine linked polymer. So, now I have told you so far what is topochemistry. Again, I am every time briefing. I have told what TAC and TEAC reaction, topochemical azide alkane cycloaddition reaction, and TEAC reaction, topochemical enazide cycloaddition reaction, which we have established. Now, we should solve some of the challenges in polymer synthesis. Regular solution state polymers, and there are problems. There are unsolved problems, or there are difficulty in some cases. Can we address some of those is what I am going to tell you in the next few slides. polymer blend. You heard of polymer blending, right? Blending a polymer with another polymer is to get properties. So you take polystyrene, you take another polymer and blend them together physically. I mean, take physically these two and mix them, and that is called a polymer blend. You are going to have better property, I mean, or interesting properties out of blending, this physical blending. The problem with the physical blending is you cannot have a homogeneous mixture. Sometimes there can be phase separation. That means your A polymer can be segregated in some places. Throughout the mixture, you cannot have a uniform structure. This is not isotropic system. So to have a better property, you should have a properly 1:1 talking to each other, right? That is the ideal system. That's impossible by physical mixing to pre-made polymers. So can we use our chemistry to make this one is a question. So in that, this one again, this is, so after trying several systems, we got this one, right? So this particular monomer, there are two molecules in the asymmetric unit. This is the same molecule, but there are two conformations. That's what it is, right? In an asymmetric unit, there are two molecules, means two conformations are possible in the same crystal, in the unit cell. So this has two conformations, and you can say conformation, conformer A and conformer B. And the top line is conformer A, and second line is conformer B. They are self-sorted. Conformer A talks to conformer A, conformer A, conformer A. Next one, conformer B, 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 like that. That is self-sorting. In the crystal, again is conformer A, again conformer B. That's good. Now you see, this one is parallel, right? The attachment is on the same side. The carbon attachment is on the same side. So that means you are going to get 1,5 linkage if it reacts. And the next line, the B polymer, it is like this. They are going to give 1,4. So there are two different linkages. And of course it is 1:1 because it's a co-crystal kind of thing. It's not a co-crystal, it's a two polymorphs, I mean two conformers in the asymmetric unit. So we reacted this one, I mean we heated. So we got two polymers, 1:1 polymer specific bending, proper blending actually. And they interact, they have hydrogen bonding in the system. Essentially these are two different polymers in the same crystal. Now, you see, it is sometimes it is a nuisance. You don't want two polymers. Yeah, solid state. Now that is the question. In solid state, you don't want two polymers. One is a nuisance for you. How do you avoid that? In solution, we use different solvent, different catalyst, different condition to avoid one byproduct, for example, or unwanted product. In solid state chemistry, you don't have those facilities, right? You cannot change solvent, you cannot change conditions, all those things. So how do we change? So we use again solid state approach, that is co-crystal approach. So actually this was the idea of my student, Hema, she is from Andhra Pradesh. So she told, sir, we could take a monomer-like molecule and make a co-crystal. And this is what her proposal was, right? This monomer is having arrowhead and arrow tail. This is monomer. The other one, this is the packing. This is the original monomer crystal. One is this conformation, the other one is other conformation. And we are getting two polymorphs. This is a nuisance we want to avoid. Now her proposal is that you take another isosteric crystal, sterically similar molecule, and that also should be like this. That we should try if there are such crystals. And then if you mix one and one, you will get a monomer layer and a dummy molecule layer. This is a dummy molecule. This is unreactive. Then we can avoid this reaction, right? The second reaction. That is what her idea was. I told it will never work. It will never work. Then she said, sir, I have done this already. So after doing this, she has told me this one, it's possible. So it's a brilliant idea, right? Yes. So what she has taken is this one. Very simple, right? You have changed this alkyne to azide. This is having a diazide. This is our monomer. Now you see, this is the crystal parameters. If you are interested in crystal parameters, alpha, beta, gamma, and ABC parameters, right? This is for the other one. Very similar. And the packing, this is the packing, very similar. The hydrogen, even the dotted hydrogen bond, you can see that forming the rectangle. Everything is similar. And that also forms two molecules in asymmetric, like in our case. So one is this and the two conformers. Exactly like this. This is also reported actually years ago, carbohydrate research. So she has taken this. So these are called isomorphous structures. Isosteric molecule, isomorphous structure. When it is a polymorph kind of thing, it's called isomorphous, right? So isomorphous structure. So two isomorphous structures. Now she has taken 1:1 and crystallized a co-crystal. And this is what she got. She got as a co-crystal as expected. And as she expected, she got this one, right? Self-sorted monomer, self-sorted dummy molecule, which will not react. Again, self-sorted monomer. Now she reacted this. So only this is the one. This is the original problem. The top one is the original problem we had. We are getting two polymers. We want to avoid that. She has taken this way. And only the monomer reacted as expected. The dummy molecule stays as dummy molecule. Now you can wash off dummy molecule because this is very simple water soluble monomer, right? This is diazide is water soluble. You can wash off after the reaction. I can get clearly the one polymer. So if we are addressing even a nuisance, we can address this nuisance of regiochemistry here actually. In solution chemistry, we use other methods. We don't have such methods, but we can use crystal engineering principles. If you're lucky, right? Because you should have similar system and it should co-crystallize. That's a very difficult thing. Yeah, we did not get that, yes. That's an interesting question actually. So the other one, right? The other one we did not get. Maybe we need some, so I asked her to try with bromo. She got a co-crystal, but after that she had to leave. I don't know what selectivity there. Maybe we should re-invite. Or dialkane is also possible. Now she has taken diazide. Maybe dialkane may give something else. Or it can be same also. Another problem. This is one problem I have told, right? Blending. The another problem is, can we get polymorphs of the polymer? Malla told about polymorphs, right? Polymorphs means a small molecule crystallizing in different forms and having different properties. Even with the example of chocolate, he has mentioned so nicely what a polymorph is, right? They have very different properties for a small molecule. Now, if it is a polymer, you can have, in principle, theoretically, you can have polymorphs of the polymer. But normal solution phase chemistry, it's impossible, as I have already mentioned, because getting one crystal itself is difficult for a polymer, right? Because of the reasons I have already mentioned, the entropic reasons and polydispersity, for example. But we can use our chemistry maybe because we can get polymorphs of the monomer. And if they are reactive, both of them are having reactive distance, then we will get polymorphs of the polymer. That's the idea we have undertaken here. I think this water is for me. So here we got polymorphs of polymer in a different way. So this is slightly different. I am coming to that actually. So this is again a leucine and alanine system, right? A monomer. And the packing is like this, right? It is stacked like this. And the reaction is between the stack. So this molecule is reacting like this, not the other way around. Now you can see this is very strained in the crystal lattice. It is in the crystal lattice and it is reacting like this, the bottom layer, and it is really wound back and forth. So this is called beta amine structure, this kind of back and forth turning in proteins. So now, since it is in the crystal, it doesn't have any other option than reacting like this, because crystal react in the way it is proximally arranged. Right? It cannot have freedom to react in a free way. So it has reacted like this. So topochemical polymerization, and that's a beta amine structure. We have the structure. Now if you dissolve this one in methanol, it goes to alpha helical, because then it can relax. In the solution, it can relax. It goes to alpha helix. Now you can remove solvent, right? You can remove methanol. Just evaporate methanol. It will retain the more stable helical form. So you have as synthesized as a beta amine form, and dissolved and evaporate is an alpha helical form. But this is not crystalline. This is not fully crystalline. So you cannot call it as polymorphs, but what I am telling here is two different solid forms of the same polymer. They may have very different properties which we have not investigated so far. Other properties. This is another system. This is the real polymorph. This diphenylalanine system having azide and alkane. We got three different polymorphs of this monomer from different systems. This is from methanol toluene, this is from toluene, this is from xylene. You can see the cell data if you are interested, or crystal unit cell data. Here they are different, and this is the powder XRD showing polymer 1, polymer 2, polymorph 1, polymorph 2, because you can see the difference between the polymorphs there. And that, this is the package. The first one of the polymorphs. So I have shown these arrows, right? The green arrow and the brown arrow. So they are not ideally in a reactive distance. I have shown an oval, round-shaped thing, right? Oval-shaped marking. In that marked area, there are two azides. One azide is here, one is here for opposite. And this alkane and this alkane. So azide and alkane are at proximity. They are not in a ready-to-react distance. But it can rotate. It can rotate. Azide can rotate and reach the alkane and vice versa. And if it rotates, it can the polymerization can be along C direction or B direction. And if you heat this one, again, I think it was at 60 degree or 70 degree, I don't remember exactly the temperature at which we have heated. And if we heat, it reacts. It reacted along the top direction, the green wave direction. And now you can see after the reaction, it is taking 2 molecules of water at each monomer site from the atmosphere. Because this rotation generates a lot of space in the crystal lattice. Usually crystal doesn't like free space. Crystal likes maximum packing, right? Packed arrangement. So when there is free space, that is not a stable system. So to avoid that free space, what it does is it takes water from the atmosphere, air. Air has a lot of water. So that water is what you see here. The 2 dots means 2 oxygens, actually they are hydrogen bonded, 2 molecules of water at each site. Now you can remove that water by heating or even blowing nitrogen or air. And you can get this upper form, for example, so without water, anhydrous form. And again you keep the anhydrous form in room temperature for a few minutes. In 6 minutes it's fully packed again with water. You can do this hydration, dehydration n number of times. Every time you get 8.2 weight percentage down, right? This is the TGA experiment showing 8.2 is the weight of water actually. So you can do repeat, you can repeat 1,000 times. I have repeated 30 times. This is the 30 cycles of hydration, dehydration. And you can see at very low temperature it rehydrates, even at room temperature it dehydrates. Now, this is very interesting feature actually, very interesting property actually. It is taking water from atmosphere. People are interested in atmospheric water harvesting. Now, current global population, only 40% have access to water. 40% of the global population has access to water throughout the year. At least, this is the data. At least a month in a year, they don't have access to pure water. And after 10 years, only 10% of that, after 10 years, it will be 9 billion. 9 billion, of which only 90 crore people will have access to water. 10% of the global population will have access to pure water throughout the year. So this is the reality we are going to face. The whole globe is going to face. So everybody is interested in either purifying water. Maybe you have heard, listened to Pradeep's talk. I was not there. He must have talked about purification of water, right? Either purification of water or getting water from atmosphere. And this is one of the important research happening everywhere. Atmospheric water harvesting. You have material which can take atmospheric water and easily release. People do usually MOF, molecular organic framework. The problem there is it can nicely coordinate water and metal. That's a problem. That's a problem because if you want to remove that water, you need to put more energy, right? You need to put more heat. And after a few heating, and you don't know whether the crystallinity of the MOF is maintained or not. Once it goes to amorphous, it may not be able to take. That is called sintering. So that's a problem. So now here we have a polymer. It's fully organic polymer. The interaction is very, very weak interaction. A hydrogen bonding interaction with a triazolyl nitrogen. Triazole, that aromatic ring, right? The triazolyl group. is hydrogen bonded with water. That's a very weak interaction. That's why we can release it even at room temperature. And it's fully organic polymer. There is no contamination of metal, all those things. But it's a very expensive material so far. It's made from pure amino acid, right? So far it is very expensive. But this is very good. And if you see the relative humidity at which it takes water, even from 30% onwards, 40%, relative humidity takes water. That means any place on earth it can take water. Even in Middle East, it can take water so easily. That is the isotherm says that. But unfortunately, we did not know the importance of this graph. We have published in this journal, and I have gone with this poster to a Gordon conference. And Michael Zavrodko, he is working on this kind of system. He said that you missed the nature. Because this isotherm at that relative humidity takes water, and it's a fully organic polymer. You simply missed the nature paper. But nevertheless, we did not know, right? So that's what happens. So what I want to say is that, so this kind of system, fully organic material, which can take water and release water at so easily, is very, very important material. Atmospheric water harvesting. And I have come to only one of the polymorphs, right? We told 3 polymorphs of the same material. This is the one I just briefly explained. So this will give anti-parallel polymer, right? One polymer is in this direction, the other one is opposite direction, then back and forth. So that is one which is taking water. The other polymorph is having 2 molecules in the asymmetric, 3 molecules in the asymmetric in the monomer. After polymerization, it becomes 2 different conformers in the polymer. So here I have shown. So the red and blue. So one is a different conformation, the other one is a different conformation. So a blend of 2 conformers. That is going to have different polymers. All of them are parallel. Arrow is on the same side. This is arrow is on the opposite side. Same conformer, opposite side, but different conformer, same side. And the third one, again, same conformer, one conformer and same side. So this is a different system. So we have 3 different polymorphs of the polymer. Chemically they are same. This is another system, again peptide based. This is a DL peptide. I mean D amino acid and L amino acid coupled together. And in this case we got 2 polymorphs as I have schematically shown here. This is parallel polymer. You can see the head is always one direction. In this case anti-parallel. Adjacent heads are on opposite direction. You can see, right? Head is this side, that side, back and forth. So they also react. And you get this kind of polymer. So this is the polymer having parallel orientation. This is the polymer having anti-parallel orientation. And this, unfortunately, we don't have the final crystal structure, because what happens is after heating, this loses its crystallinity. It becomes opaque. And this is only, schematic diagram, just based on the arrangement in the monomer. Monomer structure we have, not the polymer structure. This is a sugar monomer, inositol based. This is a very simple molecule, just protection of inositol hydroxyl group. We get 3 different polymorphs, again from different solvent, acetonitrile, chloroform, ethyl acetate, hexane, etc. Again, different packing showing different PXRD patterns, different melting points, all those things. Now in this case, so the first one, let us see the first polymorphs. There are 2 molecules in the asymmetric unit. You understand what is asymmetric unit, right? 2 molecules mean 2 conformers. Slightly there is an angle, all those things are different. So that's what it is. So conformer A and conformer B. All of them are self-sorted, fortunately. Self-sorted means conformer A is only talking to conformer A. I mean in a reactive distance. Talking, what I meant is, the azide and the alkane are at proximity. So see, this is conformer A self-sorted, conformer B self-sorted. They are 1:1, 50-50, right? So in this case, the distance is 7 angstrom. Here it is 6.8 angstrom. So you don't expect any reactivity. Our topochemical criteria says that it should be less than 5 angstrom. So you don't expect any reactivity in this case. And in this case, 2.5 molecules in the asymmetric unit. That's one of the molecules is in the special position. So the half molecule in the one asymmetric unit, the other one is in the next one. That's why 2.5. So crystallography, that's possible. So Z prime is 2.5. So A, B, and C I have named. So again, A is self-sorted, B is self-sorted, C is self-sorted. So A will react, 3.8. B will not react, 8.2 will not react, right? C also will not react, 8.8. So you expect 40% reactivity, because this is 40%, this is 40%, this is 20%. 2.5 is our Z prime. So you expect 40% reactivity. In this case, there are two molecules again in the symmetric unit. So you react 50% reactivity because one is 3.5, the other one is 7.7. So no reactivity, 40% reactivity and 50% reactivity is what we expect from the monomer structure. Actually, all of them react to 100% in a topochemical fashion. So that's the beauty of thermal topochemical reaction. The topochemical reaction people have explored until so far, until I have started work, are mainly 2+2 cycloaddition or polydice. All are shining light. You are not heating the crystal much. So in this case, I am heating. That means the distance what we see in the monomer is no longer valid because they can move. Upon heating, these molecules can move slightly. And some cases, it has even rotated. I don't have the structure today, I think. Maybe I'll see. 180-degree unreacted. So such motions are possible in the crystal lattice. Even Malla also mentioned some motions, right? Similarly. So all of them reacted. This is the powder XRD showing without losing the crystality. This data shows that until the end of the reaction, it is keeping the crystality because it's moved and reacted. This is a new system. Here, this is another interesting. So, in the previous cases, I had 3 polymorphs, right? The diphenyl, I had 3 polymorphs of the monomer. Then the DL peptide, I had 2. And the sugar, I had 3. All of them reacted and we got different polymorphs of the polymer. Now, I have only one structure of the monomer. Still, I am getting 2 polymorphs of the polymer. How? This is very interesting, actually. This is again a amino acid-based system. This is in a ready-to-react arrangement, right? You expect reactivity here along that horizontal direction because it's less than 5 angstrom and in a parallel fashion. So you expect 1,5 selectivity. This is what we expect. So because of our thermal nature of the reaction, it behaves in a different way. So it was reacted diagonally instead of in a straight line. So it has reacted with this partner. This partner reacted with the partner diagonally connected, which is at 7.7. You don't expect reactivity normally because it's very far. But it rotated, this azide and alkane rotated and reached, and it reacted along this direction. Of course, the selectivity changed. So you expected originally the 1,5 selectivity as I have shown here, but what we got is 1,4 link. So like regio-specific actually. There is no trace of other possibility. So it's fully reacted, but along this direction through the rotation because it's under heating. Even room temperature, I don't know why. Even in room temperature, this reacts. After it takes 30 days for the reaction, but it rotates and reacts, despite having a very good distance for the normal reaction. Okay, so this is the polymer. This is the polymer structure. Now, we have heated this directly in the. How do we ensure it is single crystal transformation? You may be thinking. So what we do is we take a single crystal and mount on a crystallography machine and take the data and heat there itself. In the machine itself, we can heat, and after some time we can collect it. That's how we make single crystal transformation. Okay, we don't even take out from the machine. So we have done this reaction for 4 hours of heating, and we got polymerase. Usually, before publication, we do 2-3 times to ensure that there is no mistake, right? All of you, I mean, even solution phase, we do 2-3 times, right? Especially when we are reporting something very new. So my student, she just submitted a thesis last week. So she kept for 18 hours. Actually, she kept, instead of monitoring in the night, next day morning, she's monitored. Laziness, right? That laziness gave some better results, actually. So what happened was we got another polymer. Same monomer. So it has reacted to give a polymorph, initial polymorph of the polymer. And further heating, it has changed to another polymorph. Can you imagine a big polymer, right? Polymer is so big. And it is undergoing a conformational change. A small molecule undergoing conformational change, we can understand. The whole molecule, the large polymer, undergoing conformational change, still maintaining the crystality. Single crystality. We got solid crystal data, 2 crystal data. Now we have done all kinds of experiments to ensure that, because again, we should not make mistake. So we have made the first polymer, taken out and heated for some more time, and we ensured that it is going to the second one. And in the machine we have done, so it's only the time of heating. If you heat for 4 hours, you get one polymer of the polymer. If you heat for 18 hours, you get a different polymer of the polymer from the same monomer. So we have only one monomer, two polymer. This is another system. This is another system. This is a squaramide based system. Again, we wanted this kind of chiral polymers for as a stationary phase for chromatographic separation. So we introduced a serine here, actually a chiral amino acid. So we made this kind of system. This is what is expected. Either it can have parallel stacks or anti-parallel stacks. Hydrogen bonded stacks. Squaramide is a very nicely hydrogen bonding system. So we can do polymerization along this direction. And in this case, we got two polymers, M1 and M2. And we got, we'll come to know, we'll come to that, what exactly that. Two polymers here. So one of the polymer 1, this is the arrangement. So this is the crystal arrangement. The blocks, each block is one monomer. You can see the distance, and it is ready to react to give a 1,4 disubstituted triazole linkage, right? So parallel, like click chemistry. The polymer of 2 is half helical. It is slightly twisted. The whole molecule is twisted because there is a chiral amino acid. And it is arranged again in this fashion, and you are going to have a helix actually. So this you can say supramolecular helix. It's a hydrogen bonded system. And this is like a beta sheet kind of system. Now, both of them reacted. This is the powder XRD data showing you the sharp peaks till end of the reaction, maintaining the crystallinity, both of them, at 60 degrees Celsius. This is the polymer structure. First one reacted as expected, same linkage. Both are same linkage, 1,4, 1,5. Chemically they are same. This is beta sheet kind of polymer, and this is like helical polymer. So different polymers give. One gives beta sheet kind of polymer. One is this is not alpha helical, it's a helical. Alpha helical means the distance has to be much more, closer. Yeah, this is, you can see, this is the polymer structure. The first one, there is not a helicity. Here there is a helicity. You can see there is also, during the reaction, there is an expansion and breaking of crystals. Now, another important question is polymers with the different primary structure from a same monomer. That's very difficult, right? But nature does so easily, right? For example, cellulose and glucan are coming from the same monomer, which is glucose, also starch. These all are glucose polymers, right? Here it is a regio isomer. Cellulose and glucan are, this is 1,3 connected, this is 1,4 connected, regio isomers. And these are stereo isomers, right? This is alpha connected and beta connected for starch and cellulose. So nature does this kind of mimicry, right? They can make different polymers are having very different properties, right? We cannot eat cellulose, we can eat starch. So many different properties using the same monomer. Can we use, of course, this one is another example, isoprene. Isoprene, you must have studied, right? Isoprene, the cis isoprene is natural rubber, the trans one is gataparsha, right? These are from the same monomer, nature makes in a different form. So we thought of making nylons, nylon having 3 carbons. Usually making nylon is very easy, but 3 carbon nylon is very difficult because it will undergo decarboxylation. This kind of diacid, 3 carbon diacid, undergo decarboxylation, you cannot make nylon. So we thought using our chemistry we can make nylons. Essentially we are cutting our diamine into as an alkane. So we can make nylon like this. So we thought of making this simple molecule, very simple molecule, right? So we got two different polymers. Again, this is anti-parallel, right? One is arrow is this side, the arrangement I am talking about. And this is parallel, two different ones. And the other arrangements are very similar. The distance is 3.6, not very different, 4.4. So they are reactive. Both of them are reactive. Distance is reactive. And the first case, yes, it reacted. It reacted to give 1,4 substituted polymer, as it is, like this. And it is connecting between the stacks. This is one pillar, next pillar getting connected along this direction, right? So it is in a horizontal direction, as I have shown. It is reacting in a horizontal direction. Of course, there is a bend in the polymer. That is what I am saying. I am talking about the direction. The repolymerization along that direction. In the other case, reaction is along the stacks. That means each stack react along this direction, and that gives a different stereochemistry here. This is 1,5. You remember our old problem having a nuisance, right? In the same crystal we have both. Now we have separated. Separately, 1,4 and 1,5. Yeah, separately we can make by making polymorphs of the material. Yeah, this is what it is. Helical polymers, of course, a lot of interest in the helical polymers. This I have briefly explained. This is a collagen mimic. So we got idea from collagen. Collagen has this kind of glycine, proline, and any other amino acid sequence. So we have taken glycine, proline, glycine sequence using our T chemistry. This is not tag chemistry, T chemistry. So we have taken this kind of that monomer, and it is polymerized like this. You expect reaction between the stacks. This is one stack, helical stack, because the distance between the stack is 5.9 and 6.9, not reactive distance. But between stacks, you can see here, it is 3.5 and 3.35. So you expect reactivity, as I have shown in a wavy bond in that, the corner. Actually, it did not react that way. It did not react that way. It reacted along the stacks. It reacted along the stacks. We got a helical polymer in this case. Again, the selectivity was different. We expected 1,4, but we got 1,5. Another interesting feature is depolymerization, right? There is a lot of interest to make polymers which are degradable. We can chop down into smaller fraction, which is usable fraction, depolymerizable polymers. So for that, we thought nobody has done topochemical reaction, polymerization using Diels-Alder chemistry. As I have told, Jay Kochi has done a dimerization, only dimerization, and few other papers, few dimers. We thought, can we use this thermal chemistry, this Diels-Alder reaction to make polymers? So very simple monomer. This is the diene, and this is the dienophile for us. Same molecule, right? In the same molecule, you have diene and dienophile. And fortunately, it crystallized in a fashion that it can polymerize. This is the distance between the carbons which can react. You can see less than 5 angstrom. This is not really showing there. You can see here 4.4 and 4.8 angstrom in a chain. It is expected to react along that direction. And of course, PXRD is this here, and also shows there is a large exothermic peak because this reaction is also exothermic. So it did not react as the way we wanted. It reacted fully, but it has rotated completely 180 degrees, the propargyl group, and found partner from its own molecule, right? It's an intramolecular cyclization happened. In this case also an extra water is coming from the atmosphere. Previously, you remember that in the polymer? In this case also there is one molecule of water is coming to the system, but it's not reversible, so not much use for that water. So what I wanted is a polymer. Unfortunately, I did not get a polymer, but an intramolecular cycloaddition reaction. Then we did not leave there because we want to solve this issue. So again, another molecule for Diels-Alder chemistry. You can see the dienophile and diene there, right? Furan is dienophile. Sorry, furan is diene. This melimide is dienophile. So this is the crystal packing, and between the diene and dienophile, the distance, the carbon distance is less than 5 angstrom unit, and it is expected to form polymer along this direction. And it reacts in a single crystal to single crystal fashion, again a CSC fashion. You can solve the structure. This is the polymer of the Diels-Alder chemistry. Why Diels-Alder chemistry? Triazole chemistry is, we cannot do the reversible because it's not reversible reaction. You cannot get back the azide and alkane. But Diels-Alder chemistry, of course, you know retro Diels-Alder reaction. At high temperature, it undergoes retro Diels-Alder reaction. You can get the monomers back. So that's why we have done this one. We have also shown that it undergoes at a high temperature. If you heat, it will undergo to the monomer state. because of time, and I just want to finish at 3 o'clock. Yeah, this is a CSC reaction. This I have already. Yeah, this is another system. Teak reaction. So teak reaction, again azide and alkene. You know, this is not aromatic. This group is not aromatic. This group is not aromatic means it can remove nitrogen. I told you earlier about aziridine. This triazolene, if it denitrogenate, it has two possibilities. One is aziridine, other one is an imine. Right, depending on the H shift actually. So if you have an imine, if you make an initial this polymer, triazolene polymer, and denitrogen and imine polymer, imine is very easy, right, to hydrolyze. Just put acid and you will get the aldehyde and amine containing monomer actually. So it's a depolymerase polymer if you can get that. Actually, this is again by accident, because we wanted to only make the aziridine, but we got in this case imine. I'll show you that. So this is what. So we initially reacted and we got, this is the, you can see the denitrogenation here, the weight loss. And you can see also the bubbles coming. This is in oil. If you keep the crystal in oil and heat, you can see the bubbles of nitrogen escaping from the crystal. And after that is over, you can do the structure. Now this is the imine state. This is also SCSE. Despite this much globules of, volumes of this escaped, still it is crystalline, did not rupture the crystal. And it is an SCSE denitrogenation. Then finally we have added acid to this imine and we got this monomer equivalent. It's not only, not the real monomer, right? We started with alkene and azide, but now we have imine, right? Imine to aldehyde and amine. Of course, they can also polymerize. So it's a monomer equivalent. So we have addressed a depolymerizable polymer two ways. One is using Diels-Alder chemistry and also the T chemistry. 2D polymers. 2D polymers means, 1D polymer means, of course, you understand, right? It's going endlessly in one direction. 2D polymers means what? You grow in 2 dimensions and you get a sheet. You get a sheet of polymer. So you think, is it possible by solution phase chemistry? It's impossible. It's impossible to make a 2D polymer by solution phase chemistry because it's randomly, it can make a cross-linked polymer actually. It can make a cross-linked polymer, not a 2D polymer. 2D polymer, you should be able to peel off one layer. So we can make, because we are doing reaction in the crystal and we can do reaction along this direction and this direction. If that happens, you have a 2D polymer. So this is, so of course we need 2 reactive units. Here 2 azide and 2 alkane. Very simple aromatic substance. So this has 2 molecules in the symmetric unit. You know what that is now? Small conformation difference, conformer A and conformer B. They stack one over the other. This is the stacking distance. Now between the stack you can see 3.3 angstrom unit ready to react along the stack. And between the stack also 3.8 less than 4.8, right? 3.8 and 4.8. So it can react along behind the board actually, as I have shown here, because along the stack and also between the stacks. Then you are going to get a sheet of polymers. Let's see if it reacts like this. Yeah, it reacts like that. First, so I am not explaining all this thermal data because of time. So first it reacts along the thickness. Actually, if you heat until 150 degrees centigrade, you can redo the structure. You see only 1D polymer along the thickness, along the stack. Now, if you further heat that, it will undergo reaction along the other direction. You can have both the snapshots. Monomer, 1D polymer, then 1D polymer polymerized to 2D polymer. So this is that. After the monomer polymerizes, if you further heat, you get 2D polymer. This is the 2D polymer in 3 dimensions I have shown. So the right one is the 2D layer. And you can also peel off. This is the crystal getting peeled off. If you add a little bit of acid to the solution where you keep the crystal, any solution, add a little bit of TFA, because it will get protonated, right? The triazole get protonated. Protonated means repulsion, right? Two positive charge repulsion, and it will peel off. Also, you can add methyl iodide. Methyl iodide will get methylate that one, the triazole ring, and you can peel off. The layers coming out you can see by microscopy. So these are 2D polymers. So yeah, that's what I have said. This is hierarchical. You can stop at 1D polymer, solve the structure. Yeah, also you can do the 2D polymer structure also, you can solve the structure. All single crystal to single crystal to single crystal transformation. The last example I have is a complex, stereo complex. Polymer stereo complexes means for small molecule chemistry it is a racemic mixture. So if you have an R isomer, R enantiomer, and take the S enantiomer, mix them together, what you get is a racemic mixture, right? In a simple compound. But in polymer, you don't say racemic mixture because, as I said, polymer has all kinds of length, right? You don't have a specific length. So even if you mix the equal amount, you don't know whether it is a perfect cancelling each other. No. So people say it's stereo complex. You take R polymer having R chirality in all the monomer unit, and take the S chirality and mix them together, and you are going to have better properties. These are called polymer stereo complexes. As I said, a perfect blending is impossible. In the previous cases also mentioned, right? Blending is always difficult, physical blending. So, yeah, so this is what. You take S enantiomer pure polymer, R enantiomer pure polymer, mix them together. Ideally, what you want is this one, this place, this location. A perfect blending of one color with the other color. I mean, color-coded actually. And reality, what happens is the whole thing, right? It has all kinds of coiling and self-segregation, all those things. It's not a perfect blend. But using our chemistry, we can use topochemistry to get better blend of this stereo complex. So we have taken an achiral monomer. This is not chiral actually. This is a meso derivative, but it will crystallize in a conformational enantiomers actually. So it will form a conformational enantiomer in the crystal. So this is one conformation, the opposite conformation. They are mirror images. Right, there is no plane of symmetry in the crystal. But in taking solution, of course, they are randomly mutated, you can draw a plane of symmetry. So they are conformational enantiomers, they are self-sorted. That means R form always talk to R form, S form always talk to S form. So if you do reaction, you get a polymer with same chirality in one chain. Next chain will be opposite chirality. That is called stereo complex, perfect stereo complex. This is what we got here. This is an SC-SC reaction again, single crystal to single crystal polymerization. Again, I have color coded. This is one chain, going behind the board, several chains in one stack of the same chirality. The blue chain then comes, same chirality, they are alternating actually. So also in this way you can see, this is one chain, polymer with the same chirality, the other one is opposite chirality, again back and forth it is, right? So it's a perfect stereo complex we have made using our crystal chemistry. I should have detailed much more than this, but because of time, but if you have any question, I'll be happy to answer. So what I have showed you is, yes, topochemistry can address some of the problems in polymer chemistry. Of course, you can make crystalline polymers. I have shown you several crystalline polymers. Also, I have showed you two polymers in a single crystal. Also, two structurally different polymer in a monomer. That means different chemistry, right? And polymorphs of polymer, several cases I have shown. Helical polymers I have shown. I have also shown two cases of 2D polymerizable polymers. I have shown one example of 2D polymer, but I have 2-3 more to report. Actually, we have few results in the lab. And polymer stereo complex also we have one more to report. One I have shown. And these are all the problems in the solution phase chemistry, polymer chemistry. So all these guys have done this reaction, I only go and speak. So these guys have graduated out of the lab. They're in different parts of the globe. This guy is going to Cambridge with Jonathan Nishke as a Marie Curie Fellowship soon. In February he's going. Anu, I think Anu is there. She just submitted the thesis, and she's the one who found this, who forgot to do the collection in the night, and she got a better results. And now she is attending a conference in Nagpur. Actually, National Crystallographic Symposium is happening now, today and tomorrow. It's happening. She's there. And Haripriya, I think she's the one. She got the 2D papers. And Sijil is already out of the lab. He is in Brandeis University now. He finished even one postdoc, and he's also a Humboldt fellow now. He got a Humboldt position. Few of them, about 3 of them got Humboldt, 3 of them got JSPS, and 2 of them got Marie Curie Fellowship. They are doing well. So finally, thank you all for your invitation and attention.
Thank you, Professor Sureshan, for the excellent lecture. Now the session is open for discussion. Probably a couple of questions may be permitted. Yeah.
So, congratulations, Professor Sureshan. It's a wonderful work, and thank you so much.
Thank you.
I do have a few technical questions. I mean, practically, how do you follow this polymerization and technically in the lab? I mean, by using TLC, what kind of?
Yeah, so we only do the crystal structure and also DSC. I have shown DSC, right? So regularly, how you for TLC we cannot do because they are not soluble, right? They are not soluble even halfway through. Also, they are not soluble, and polymer cannot rise also in the TLC. So we do, when it is T chemistry, TAC and T chemistry, we have azide. That can be monitored by solid state IR. So every now and then we take, after regular intervals, we take record solid state IR and see the decrease of this one, azide secret. That is one, and also we do powder XRD. I have shown the time dependent powder XRD. It's all the way we do the monitoring. And what we initially do is heat and see if it is dissolving or if it can solve the crystal structure. So usually sometimes we get directly polymer. Then we study all these kinetics, etc. later using these techniques.
Okay. And if you have multiple azide groups in the molecule, isn't it explosive or is it stable?
So there is this one, carbon nitrogen ratio. If it is 1:3, is better than 1:3 is always safe. 1:3 is okay, 1:2 is bad. So we have more than 1:3. There is no issue. Carbon nitrogen ratio is the one which decides the explosiveness.
Okay, okay. About this DNA analogs, cytosins, triazole, is it comparable with the PNAs, peptide nucleic acids, or how is it?
Yeah, so this is one thing we wanted to do. We never did that actually. So a melting study with a complementary normal DNA, right? So these are stable in terms of the linkage. They are much more stable than PNA and also DNA. Now, the Isobe, the guy who has made the solution phase 9mer, he has done a melting study, taking a complementary T, A and T. He has C and G, right? C and G. He has taken G and did a melting study, UV melting study. And they found that it is much better than DNA and DNA RNA. And PNA he has not tried. So we have not tried that because our problem is, as he mentioned, we cannot have a specific length to take a complementary pair of the same length. So that's our difficulty. We haven't studied that.
Okay. About this beta galactose sugars, is it specific towards beta only or what about alpha anomers?
Can we make polymer? Yeah. We have made so many alpha also, mainly glucose. Also, mannose is difficult. Alpha also possible. Alpha galactose we did not try. So galactose beta is easy to make. That's why you have to.
Okay. Thank you. Thank you so much.
Sir, this regarding the kinetics mechanism and electronic structure. Actually, the gaseous phase reactions used by the theoreticians to predict the mechanism of solution phase reactions, some of the. So here the kinetics, how far we can proceed with the kinetics, the reaction mechanism, the bond formation, electronic structure. I mean the electronic structure behind the.
Maybe we have to talk to the theoreticians. We never did that. Okay. We never did that, and we never got such harsh questions so far from referees. But we do the kinetics, experimental kinetics we do using, wherever solubility is there, we do NMR. Okay. Using NMR we can do the kinetics.
Okay. It is clear why the crystal is taking in water because of the space, but what drives it to dehydrate?
Heat or blowing nitrogen with the pressure.
You will have to, okay.
Yeah, so it's just compressed air is fine. So there is a pressure. So through the crystal it goes.
Oh, okay.
And it's very weakly hydrogen bonded. Otherwise heating less than 50 degree it takes.
Hi, sir. Yeah. Sir, you are doing topochemistry for development of polymer. Can you use topochemistry for development of molecule? Like two different crystal will take and do the, like one having alkyne and one having azide. Then two reaction can happen. Like one molecule, one functional molecule we can develop in such a, like instead of all the things you have is to one alkyne and azide in a single molecule do the polymerization. If two crystal will take.
No, not two crystal, two molecules I can take. Yeah. Two crystal is difficult, right? Because then one molecule is all ensemble of one molecule is in one crystal. Okay. All billions of molecules in another crystal, and they will not react. They are crystals, right? So you can take two molecules, do a solution phase co-crystallization. Okay. If they are co-crystallizing. Okay. If you are lucky, only that will happen because it has to be identical molecule, identical solubility. All those issues are there. If you can co-crystallize, I have shown some examples. We also have some examples which I did not show you. Okay. You can do A plus B reaction to make a dimer, but it has to be a co-crystal. You cannot take one crystal and another crystal to react them because the gap between them we don't see, right? The air gap. Air gap is trillions of molecules away actually. If you put two crystals together, there is a small air gap between them which you cannot see. Yes. That is almost trillions of molecules between them. So that much molecule it cannot catch, right? So it's impossible.
Okay, but if you will do co-crystallize, we can. Yeah. Yeah. Okay. I think that one we.
Okay. Yeah, one last question, please.
My concern is it possible to can make an intramolecular track reaction?
Yes, I have shown one example. It's an accidental reason, right? TAC reaction, right? Yeah. TAC reaction, the problem is whatever intramolecular tackable molecule, it already react in the solution phase itself. For example, we had a azide at the anomary position of the glucose, right? And an alkyne at the second position. So while we made the molecule itself is already polymerized. I mean, intramolecular cyclization happened because that's a 6-member ring you are making. So that's easy. Intramolecular reaction is much more faster. So unfortunately, TAC we did not see. I mean, we could not investigate that because already that's reactive. Azide and alkane, when they are separated by 6 bonds, they will react in solution itself. But in the other case I have shown, it is rotating and the yields are reaction.
Sir, is it because like your molecule had an anti-relation between the alkynic attached carbon and the azide carbon? Is it because since it's anti, it is not reacting in that fashion?
Anti?
Like one was in alpha plane and the azide was in the beta plane.
Huh.
Is that could be substantiated for reason for that reaction not happening?
Which case you are talking about?
The TAC reaction only.
So, no, TAC reaction is happening. I mean, which
like within the molecule, intramolecule.
Even if it is anti, it will react. 6-member ring, it can form this one, right? Translinkage is fine. Okay. You are not making a double bond inside, no? That's okay, fine.
Thank you, sir.
Yeah, I think we should wind up here.
Okay, thank you. You have a question?
One last I will ask questions during the tea break, but I have one question. You have mentioned that this topochemical polymerization has explored in photochemical mainly, and you had tried to do the 4+2 thermal condition with fluorine malamide, where it was an intramolecular reaction you tried. What is the possibility of intermolecular in that case?
No, intermolecular only we have shown, right? It's a polymer actually we got. The other one was anthracene and this propagylate. That we wanted inter, but reacted intra. It's a nuisance actually, but still we made a good paper out of it by showing the mechanism and all those things. But that's a difference. That's not what we wanted.
Yes, okay. That I missed. Okay, and thank you very much once again on behalf of our entire audience. I please join me in congratulating.
Thank you very much.
And wish you all the best for the future. Thank you.
Thank you, sir, for this enlightening session. Now, I invite Dr. S. Anes to hand over the memento to Professor Kanayam Sudeshan as a token of love. I invite Professor Sudeshan to receive the same.
Everyone sleep? Good.
Thank you, sir. With this, all the plenary lectures of this national seminar have come to an end. Now we are moving on to the valedictory function. I request Chief Guest of the Day, Dr. S. Anis, and other dignitaries to occupy the dais.
Good afternoon, respected dignitaries, distinguished guests, faculty members, and dear participants. As we come to the conclusion of the 23rd Professor K.V. Thomas Endowment National Seminar on Frontiers in Material Sciences, it's my privilege to welcome you all to the valedictory function. Over these 2 days, this seminar has been a remarkable platform for sharing knowledge, exchanging ideas, and fostering collaborations in the fascinating field of material sciences. To formally welcome everyone to this valedictory function, I invite Dr. Gina George, Associate Professor, Head of Chemistry Department, and the convener of this national seminar to deliver the welcome address. Ma'am, please.
Good afternoon. Respected Chief Guests, Dr. S. Anas, Kiley Research Awardee, Reverend Dr. Verghese Kachapalli, Manager of Sacred Heart College, Principal Professor Dr. C.S. Biju, Vice Principals, the visionary Professor K.V. Thomas, he will join us soon, faculty members, students, and well-wishers. It is my honor to welcome you all to the valedictory function of 23rd Professor K.V. Thomas Endowment National Seminar on Frontiers in Material Science. Over the past 2 days, the seminar has been a vibrant platform for exploring the latest advancement in material science with a focus on sustainability. Esteemed speakers, including Padma Shri Professor T. Pradeep, Professor Sebastian C. Peter, Professor Challa Malla Reddy, and Professor Kana M. Sureshan enlightened us with groundbreaking insights into their research, inspiring rich academic discussions and innovation. I take this opportunity to extend a special welcome to our chief guest, Dr. S. Anas, recipient of the Kairali Research Award, whose achievements in research bringing prestige and honor to this event. Welcome, sir. A warm welcome to our principal, Dr. C.S. Viju, whose steadfast support has been integral to the success of this seminar and all our academic endeavors. Thank you, sir. Welcome, sir. I also welcome our Vice Principal, Dr. Franklin John, and Father Kusumalayam to this function. Welcome, sir. A heartfelt welcome to Professor K.V. Thomas in his absence, whose vision and generosity have made this endowment seminar an enduring platform for academic excellence. Welcome to the convener and the heart and soul of this program, Dr. Ammu Rosin Jos. The seminar also showcased oral and poster presentations by talented researchers and students, reflecting the academic rigor and enthusiasm within our scientific community. However, I take this moment to sincerely apologize for the delay in concluding yesterday's poster evaluations. The judges, adhering to fairness and excellence, required additional time to ensure the best outcomes. We regret any inconvenience caused and sincerely appreciate your understanding. We are deeply grateful to all our sponsors for their generous support, which has been instrumental in making this seminar a grand success. On behalf of the organizing team, I extend heartfelt thanks and welcome to all our guests, delegates, participants who joined for this academic celebration. A special note of appreciation to our former teachers, faculty and staff whose guidance and encouragement continually motivate us. Finally, I welcome everyone to this valedictory function where we will celebrate the achievements of the seminar, recognize outstanding contributions and conclude this enriching journey. Thank you, and let us now proceed with the valedictory proceedings. Thank you.
Thank you, ma'am, for your warm and gracious words of welcome. We are honored to have Professor Biju CS with us, the principal of Sacred Heart College, Thevara. I invite sir to deliver the presidential address.
Good afternoon. We are in the concluding session of a very successful, wonderfully organized, amazing academic conference. I'm very happy that we have a very eminent scientist and academician, Professor Anas, with us for the concluding session. I don't have much to say. We are waiting for our dear Professor K.V. Thomas to come. First of all, I wholeheartedly congratulate the wonderful academic community of the Department of Chemistry at Sacred Heart College. Under the eminent leadership of Dr. Gino George and a very vibrant, enthusiastic, rigorous group of people whose academic persuasions go far beyond our imagination. This department is actually an exemplary example, a wonderful example to any academic department in India. The whole department and its students have been working so hard for the last 4 months to accomplish this effort. I congratulate each and every member of the volunteers team, teachers, research scholars, again and again. we have a wonderful participation from various academic institutions, universities, etc. At the same time, we have a wonderful bunch of resource persons who are internationally known, though this is named as a national conference, including the renowned luminaries in the field of chemistry, nanoscience, material science, etc. I'm immensely thankful on behalf of Sacred Heart College to all the great resource persons who joined us, who collaborated with us for the success of this amazing program. And as everybody knows, this is the 23rd Endowment Conference, alternatively international and national. This is actually the actual fire behind this is an eminent statesman, teacher, and professor, Professor K.V. Thomas, who served as the head of the Department of Chemistry. Before that, he was a student of this institution. And he is, after 23 years of his retirement, he still remains as a wonderful inspiration for everybody in the Department of Chemistry. I acknowledge his inspiration, his support, the kind of rigor he imparts to us. I'm immensely thankful to Professor K.V. Thomas on behalf of Sacred Heart College. I wish next time we'll have another wonderful international conference in a very relevant field of chemical sciences. I wish everybody, all the participants, students, teachers, everybody, all the success. Thank you very much.
Thank you, sir, for your inspiring words.
I've forgotten to mention one name, a very young academic who is instrumental in shaping up the whole project is Dr. Ammu Rosen-Jos. Congratulations.
Thank you, sir, for your inspiring words and for being the guiding light behind the success of this seminar. Moving forward, it is with great honor that I invite our chief guest, Dr. S. Anas, recipient of the Kairali Research Award for 2022-23 and the Associate Professor at Mahatma Gandhi University, Kottayam, to share his thoughts with us. Sir, please.
Good afternoon to all. Respected Principal Dr. Biju, Head of the Department Jinu, and the convener of today's program, Dr. Ammo, and other faculty members and my dear students. First of all, I would like to thank the organizers for inviting me and giving me an opportunity to be a chief guest for this wonderful conference. And thank you very much. And from my heart, I would like to congratulate the entire team behind this conference for making it as a grand success. Because as an academician, if you are looking into various conferences and seminars going on in the state, I can undoubtedly say that it is the one of the best conference among organized in the state of the Kerala. Because for the last 4 or 5 years, I am continuously visiting this college and attending the conferences and seminars. I can see that, and they are keeping this quality in terms of the lecture and in terms of arranging the programs. As rightly mentioned here, when we are organizing seminars and conferences, what we are expecting from that conference. It is not merely listening to the lecture, it's not merely giving some awards. Instead of that, those who are attending the seminar should be motivated and should have a trigger to do the research and do more better research in the future time. In that aspect, I feel that, especially in the last session, I was chairing the plenary lecture. I can see that none of them were disturbing, completely attending the session for the last 1.5 hours. 1.5 hour. Therefore, I believe that the seminars like this should be repeated, and the students from different institutions and the different colleges and the university should get a chance to participate here, and they are giving this chance continuously over the years. I'm happy that in that way it is a success. I would like to point one thing, that already in the introductory section, in the welcome speech, Dr. Jinu mentioned that yesterday something happened regarding the arrangement of the time scheduling. I should mention that because that is the only concern I can feel from the organizing, from this year's program. It was extended up to the 11 o'clock in the night. I should mention this here, at least in the validatory section. We have to ensure that we are organizing a conference that should not exceed in that limit. Because I don't know how to express my concern here, and whatever be the explanation, and that should not happen. I hope that the college has taken that in a serious manner, and I hope that will be considered in future also. And I have been given only 2 minutes here to talk to you. I taken more than that. I don't know how to express my feelings here, because being a chief guest in this college, I have mixed feelings. All the teachers are my good friends, and that is why, even though I am not an alumni of this college, I feel like coming back to my college again. And once again, thank you very much for inviting me, and wish you all the best for the students who are presented here. Let us move on to the further session in this. Thank you very much.
Thank you, Dr. Anas. The moment now let's hear a feedback of oral presentations from our jury members. I invite Dr. Rajesh K. to view his comments on.
Respected dignitaries on the dais and off the dais. So now I think this is a time of excitement, because 2-day national seminar has been at its end, and I got the opportunity to be a part to judge the presentations, paper presentations from organic chemistry, material science, polymers, mainly on biopolymers, then green chemistry and wastewater management. So to speak about so I am here to speak on to provide a feedback. So what I felt was like, the presentations were really good, and of course it was really I also could gather a lot of knowledge from various areas, and we have presentations from the institutes, not only nearby from central institutes, as well as few from outside Kerala, and it's good. It's a good sign that everyone focused on the idea of sustainable development. So it's noteworthy to mention that this is what is required and is expected for a good future, because we all are working together, the researchers working together to aim to achieve the goal of sustainable development. And all these presentations were on those lines, and this is really wonderful. And of course, the material science and organic chemistry, then green chemistry with a lot of stuffs, they all come together for making this goal successful. And the researchers are in a real line, and you are, I mean, those who have presented, we are really looking forward to you because you are the next generation scientist. You have to lead the nation. So that is what the feedback that I wanted to provide, and it was really a great experience. And let me congratulate the organizing committee, the Department of Chemistry here for organizing this wonderful seminar in the name of our Professor K.V. Thomas. Thank you very much.
Thank you, sir. Next, I invite Dr. Radish K. to share his feedback.
Honorable dignitaries on and off the dais, young scholars. Being part of the judging team, overall, we were very impressed with the quality of the presentations that were made here. And it is noteworthy to mention that most of the research scholars who had made the presentations were very clear on what they are presenting. And one standout aspect that I would like to mention is the enthusiasm that they have brought to the subject matter. They were not just discussing information, but they were really enjoying, in sharing the discovery that they have made. And that is what makes science interesting. So thank you very much, all young scholars for making that. And I'll also like to thank the organizing committee, Department of Chemistry, Sacred Heart College, for creating an opportunity for young scholars to present, and also personally for giving me an opportunity to get exposed to such wonderful works. And then, I also need to mention that as the number of, prizes would be limited, it would be very hard to, give a prize to everyone who had presented, excellently. So a few parameters would have been, we had to consider a few parameters, to select a few winners. It doesn't make, people who have not won, it doesn't make their work inferior in any way. It's just that we were forced to make the selection depending upon the number of prizes. I also take this opportunity to congratulate all the winners. I hope the name of the winners will be announced soon. So thank you again. Thank you very much.
Thank you, sir. We would like to express our gratitude to these judges by giving them away a small token of appreciation. I request Dr. Ramakrishnan S., Assistant Professor, Department of Chemistry, Sacred Heart College, to give away these mementos. First, I would call upon Dr. Rajesh K. Dr. Radish K, please. Thank you, sirs. The moment we all have been waiting for is here, the prize distribution ceremony. I invite Dr. Thomas Kuti-Jose, Assistant Professor, Department of Chemistry, Sacred Heart College, to give away and announce the winners. So.
Good afternoon, everyone. It is my pleasure to announce the winners of the Best Poster and Oral Presentation Awards. This year, we received an incredible responses with 65 outstanding oral presentations and 31 posters. We extended our heartfelt gratitude to our sponsors, the Royal Society of Chemistry, the American Chemical Society, and elsewhere for sponsoring 18 Best Oral Presentation and Poster Awards. A special thanks to our panel of judges, Dr. Radish K., Dr. Bibin Aib Thomas, Dr. Paulson Matthew, Dr. Rajesh Kunjambali, Dr. Prathapan, and Dr. Leena for their valuable suggestions, comments, and time. I also thank Dr. Ramakrishnan S. and our fellow colleagues for their invaluable support throughout this event. Without further delay, let's announce the winners. I request our chief guest, Dr. S. Anas, to hand over the certificate and cash prize. Please, sir. The Best Poster Presentation Award, sponsored by ACS Sustainable Chemistry and Engineering Journal, goes to Ninu K.V., Cochin University of Science and Technology, Kusa. Ninu K.V., Cochin University of Science and Technology, Cochin. Okay, next. ACS Sustainable Resource and Management Award goes to Vidya K.V., Union Christian College, Alua. Vidya K.V., Union Christian College, Alua. Anybody from Union Christian College? No. Anybody from UC College, Alua? Okay. Next award, ACS Crystal Growth and Design goes to Rohit R., SD College, Alapura. Rohit R., SD College, Alapura. Next is ACS Inorganic Chemistry goes to Sujisha S. Nambiar, IIT Guwahati, Assam. Sujisha S. Nambiar, IIT Guwahati, Assam. Next award, Elsewhere Flat Chem Journal goes to Anu Pulparambil, JNCSR, Bengaluru. Anu Pulparambil, JNCSR, Bengaluru. Next, Elsewhere Flat Chem Journal award goes to Sona Saji, Government College for Women, Vadakad, Thiruvananthapuram. Sona Saji, Government College for Women, Vadakad, Thiruvananthapuram. Next, RC Materials Advances goes to Siddharth K.S., Central University of Tamil Nadu. Siddharth K.S., Central University of Tamil Nadu. Next, RC Materials Advances goes to Gobiga K.Y., Government Victoria College, Palakkad. Gobiga K.Y., Government Victoria College, Palakkad. Next award, RC Materials Advances goes to Sunitha Saha, Indian Institute of Technology, Vilani Durg, Chhattisgarh. Sunitha Saha, Indian Institute of Technology, Vilani Durg, Chhattisgarh. Next we move on to the presentation of oral presentation awards. And ACS Sustainable Chemistry and Engineering goes to Devi Krishna KS, CSR NIIST, Thiruvananthapuram. Devi Krishna KS, CSR NIIST, Thiruvananthapuram. Next is ACS Sustainable Resource and Management goes to Srijit S, CSIR NCL Pune. Srijit S, CSIR NCL Pune. Next is ACS Crystal Growth and Design Award goes to Geeta Anbalagan, Savitha University, Chennai. Geeta Anbalagan, Savitha University, Chennai. ACS Inorganic Chemistry Award goes to Bhavya V, CSAR, NIST, Thiruvananthapuram. ACS Inorganic Chemistry Award goes to Bhavya V, CSAR, NIST, Thiruvananthapuram. Next is Elsewhere Flatcom Award goes to Bini Abraham, Cochin University of Science and Technology, Kalamassery, Kochi. Bini Abraham, Cochin University of Science and Technology, Kalamassery, Kochi. Elsewhere Flatcom Award goes to Sanjuda R, National Institute of Technology, Tiruchirappalli. Sanjuda R, National Institute of Technology, Tiruchirappalli. RC Materials Advances goes to Vinitha PK, Mahatma Gandhi University, Kottayam. Vinitha PK, Mahatma Gandhi University, Kottayam. RC Materials Advances goes to Vinitha PK, Mahatma Gandhi University, Kottayam. RC Materials Advances goes to Sri Lakshmi, Amrita Vishwavidyapitham, Amritapuri Campus, Kollam. Sri Lakshmi, Amrita Vishwavidyapitham, Amritapuri Campus, Kollam. RC Materials Advances goes to Anupama Vijayan, Central University of Tamil Nadu. Anupama Vijayan, Central University of Tamil Nadu. Thank you, Anas sir, and congratulations to all the participants. Thank you.
Congratulations to all the prize winners. Your hard work and dedication have truly paid off, and we are proud of your achievements. Also, as a token of love and appreciation, I request the principal, Dr. Biju CS, to hand over the token of love memento to our chief guest, Dr. S. Anas. A gentle reminder to all the prize winners. You all are requested to sign your vouchers from Dr. Ramakrishnan S. outside the hall by the counter after the ceremony. Thank you. Next, let's hear from some of the participants about their experiences during this seminar. I request one or two participants to come forward and express how they felt during the seminar.
Respected dignitaries on and off the dais, and my fellow participants, good afternoon all. My name is Aghila MJ. I'm from St. Thomas College, Thrissur. I'm very fortunate to stand before you to share my thoughts about this today's seminar. First of all, I would like to congratulate the entire organizing committee behind this national seminar, because all the process from the registration till this valedictory session was so beautifully arranged. Everything was very perfect and clear. Especially if we have any doubts or queries when we ask in the WhatsApp group also, they replied in a very good sense. And all the arrangements, including the refreshments, was very good. For this, about the sessions yesterday, I feel so grateful to listen from Professor Pradeep sir class about the micro droplets. That was very fascinating and interesting. And then later, we listened from Professor Sebastian sir's class Sir's class was really motivating for all of us. Sir mentioned that he started everything from the zero and he made a kingdom in his field. So that motivated us very well. And I participated in the poster presentation. Even though it was a long wait and we got many queries from the judges, but everything happens for good reasons, and it made us to think much delightful insight. And I think it would very helpful for all of us, even though it lasted for long. For each participants, I think they took a minimum of 20 minutes or 30 minutes. But thinking about that, it was a very nice experience. And then today's class, the first one lecture was Professor C.M. Reddy sir's class. That was very interesting about the crystals. And then later, Professor Kanayam Sureshan sir's class, that was also indeed, even though after the lunch the class was arranged, it was not much boring. The session was very good. And I would like to express my deep sense of gratitude to all the organizers, especially the chemistry community, and especially to all the students of the chemistry departments. I don't know whether they are undergraduate or postgraduate, all the students and the research scholars. Everybody was there all the time to assist for anything. And that's really appreciable that they were there. If we want anything, they were there in the way they are treating just in a 7-star hotel and all. I felt like that because they were assisting all the time. They are just like a shadow that what you want, what else you want, or do you need any help like that. That was really appreciable. It's not much easy to handle everything like that. And yesterday night, when we were in the corridor, that Ramakrishnan sir was there. He asked about what about the things are going and how everything is there. Then I felt very happy and a homely feel that when he asked about the seminar and all. And I felt very happy for all the faculties and all the arrangements happened here. Once again, thank you all and congratulations to all the winners. And I wish everyone all the success, and I wish everybody for the bright future, and thank you all.
More feedbacks are welcome. If anyone wants to speak, please come up.
Respected dignitaries on and off the dais, my fellow delegations and the organizing committee members, greetings to you all. I am Siddharth, pursuing my final year Masters in Chemistry at Central University of Tamil Nadu. So the major driving force that made me to register for this conference was two gentlemen, Professor T. Pradeep and Professor Kanayam Sureshan. As soon as I saw the invitation from my HOD forwarded the invitation of this conference, so I saw these two gentlemen as the plenary talk invitees. I decided I am anyway going to attend this conference because from my UG itself, I was so passionate to work under their guidance for internship. But I didn't get an opportunity, so at least I thought I'll come here and I'll interact with them. So that was the driving force for me to attend this conference. And the conference was beautifully organized. The lectures were so nice that we would take home so many take-home messages. You go with a bunch of scientific ideas and I visited the posters, and the posters were actually a diverse pool of scientific thoughts were presented in the conference. Also, I attended few oral presentations. Completely diversified areas were discussed. We take home, not only me, I feel like all the delegations and the participants and even the students of this college take home so many scientific insights from this conference. I really thank the organizers for providing me with such opportunity. I wish this novel venture is continued for so long. So I should also thank Professor K.V. Thomas in his absentia for initiating such kind of scientific temper within the students. Thank you all.
Thank you for sharing your valuable feedback. It is heartening to hear such positive responses, and it motivates us to strive even further for greater success. To formally express our gratitude to everyone who made this event so possible, I now invite Dr. Ammu Rosen-Jose, Organizing Secretary of the seminar, Assistant Professor, Department of Chemistry, to propose the vote of thanks.
Thank you. Good evening, everyone. On behalf of the Department of Chemistry, Sacred College, it is my privilege as the Organizing Secretary of the 23rd K.V. Thomas Endowment National Seminar to deliver the vote of thanks for this two-day national seminar. I would like to begin by expressing our heartfelt gratitude to our management, our manager, Reverend Father Verghese Kachapalli, our bursar, Reverend Father Tommy Palati, our principal, Professor Biju CS, and our vice principals, Reverend Father Dr. Joseph Verghese Kusmalayam and Dr. Franklin John, for the unwavering support and guidance. The encouragement and leadership have been instrumental in organizing this event. Thank you, the management. A special mention goes to Dr. Franklin John, who, despite his recent return from a prestigious 4-month visit to the Nobel laureate Ada Yonath's lab, dived headfirst into the seminar preparations. Thank you, sir, for your remarkable dedication and support. We were honored to have Professor C.T. Aravinda Kumar, Vice Chancellor of Mahatma Gandhi University, as the chief guest for the inaugural session, and Dr. P.K. Pujari, former Director of Radiology and Isotope Group, as one of our speakers. I thank them for their presence. My sincere gratitude to all our distinguished speakers, Padma Shri, Professor T. Pradeep, Professor Sebastian Peter, Professor Chalamala Reddy, Professor Kana M. Sureshan, and our session chairs, Dr. N. Manoj, Dr. Sindhu Matai, Dr. Anas, for the support. A special congratulations to Dr. Anas for receiving the Kairali Research Award 2022-23 and for gracing our valedictory session as the chief guest. Thank you, sir. We owe our gratitude to Professor K.V. Thomas, whose endowment and guidance continue to inspire this annual seminar series. I extend my thanks to the exhibitors for showcasing the innovations and to our sponsors, Sir BRNS, Cochin Shipyard, BPCL, Interfield Laboratories, MPDA, Coconut Development Board, Nairo Research, Sinsel International, Calgon Scientific, Nice Chemicals and Spectrochem Limited for the general support. A special thanks to MPDA and Coconut Development Board for setting up engaging stalls. A special thanks to our judges, Professor Prathapan, Dr. Paulson, Dr. Vipin, Dr. Ratish and Dr. Rajesh, as well as Dr. Leena, for the fair and thoughtful evaluation of oral and poster presentations. To all our participants, your enthusiasm and engagement brought vibrancy to this seminar. Even amid the tight schedules, thank you for your active involvement. I also extend my gratitude to the School of Communication for the technical support, the college superintendent office staff for the assistance, the security and canteen staff for the timely help, and the IQC team for managing the website, online registrations, and abstract submissions. As the saying goes, a team is not just a group of people who work together, it is a group of people who trust each other. My sincere thanks to Team KVT 2024, which includes our former teachers, colleagues, supporting staff, alumni, and students for the incredible teamwork. I especially thank our head of the department, Dr. Jinu George, whose vision and meticulous planning have been the backbone of this seminar. From identifying speakers to ensuring every detail was accounted for, her sleepless nights have made this event a success. Thank you, ma'am, for your dedication. We had various committees for organizing this event. I thank various committees. The Finance Committee led by Dr. Midin Dominic CD, Dr. Deepak D. Prabhu, Dr. Ramakrishnan S. for expertly managing the finance affairs. The Reception and Venue Management team led by Dr. Grace Thomas and Mr. Senju Devasukuti for the warm hospitality and management. The program committee led by Dr. Franklin John, Dr. June Syriac and Dr. Ebi TG for coordinating the seminar schedule and arrangement seamlessly. The registration committee led by Dr. Ignatius Abraham and Dr. Thomas Ukuti Jose for the efficiency in managing materials and registration. The technical committee led by Ebi TG and Dr. Jason MJ for ensuring flawless technical execution. The hospitality and transportation team led by Dr. Shalomon KT, Dr. Deepakti Prabhu and Dr. Jason MJ for ensuring our guests were comfortable. The food committee led by Mr. Senju Devasukuti and Dr. June Syriac for managing the food arrangements so wonderfully. The publication team led by Dr. Thomas Ukuti Jose and Dr. Ramakrishnan S for the hard work and abstracts and presentation arrangements. Thank you, all the committee members, the leading teachers, all the student volunteers involved in these arrangements. A special thanks to Dr. Shalomon KT for ensuring the event was well documented with photographs. To our PG and UG students who were served as volunteers, your tireless efforts have not gone unnoticed. Thank you for your commitment. My heartfelt thanks also goes to the family members of our team for their patience during these hectic days. Lastly, I bow my head in gratitude to the Almighty for His abundant blessings and guidance throughout the journey. Thank you everyone for being part of this event and making it a memorable success. Thank you all.
Thank you, ma'am. Ladies and gentlemen, as we draw this wonderful seminar to a close, let's stand together for the national anthem.
Janagana mana adhinayaka jaya he Bharat bhagya vidhata Punjab Sindh Gujarat Maratha Dravida Utkala Vanga Vindhya Himachala Yamuna Ganga Ujjala Jaladhi Taranga Tava Shubha Name Jage तब शुभ आशीष मांगे गाहे तब जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे.
Thank you. Please be seated. Today, we close the book of this chapter, Professor K.V. Thomas Endowment Seminar, National Seminar. Let's take this inspiration and knowledge we have gained from here to build brighter futures tomorrow. On that note, we come to the end of the valedictory ceremony. I hope these 2 days have been as enriching for you as they were for us. Please join us for tea before you depart. Safe travels and see you again for future events. Thank you. A kind reminder to all prize winners, you all are requested to sign the vouchers outside the hall by the counter. Dr. Ramakrishnan S. will be there to assist you. Thank you.